Dear old friends and colleagues, it is with great pleasure that I, Andrea Valle, together with my colleagues Stefano Bassanese and Marco Masoero, the two other chairs of this conference, welcome you all to the Sound and Music Computing Conference 2020. For the occasion, I have an official t-shirt from 2010. So, welcome to Torino. Are we in Torino, as the banner up to over my head says? Well, yes and no, evidently. Of course, the COVID-19 situation has forced us to change our plans for this edition. And given that it was plainly not possible to organize a physical conference, we had two possibilities. First, simply to postpone the SMC 2020 to 2021. Second, to turn it into a virtual conference. Both solutions had their pros and cons. We really wanted to organize the SMC summer school and the music program with live concerts. We were in the middle of discussing details of the contents of the school hosted by the Polytechnic School of Torino, chair being Marco Masoero, and we were going to set up 6 concerts organized by the School of Electronic Music of the Conservatory of Torino, chaired by Stefano Bassanese. In relation to this situation, the conference virtualization would mean a loss of opportunities for our community. Better to postpone. But on the other side, thanks to the work of the scientific chairs, Simone Spagnol and Caralan Possaitis, we had already collected and reviewed the scientific contributions for the conference. To some extent, they could have been presented to the community over the internet, while on the contrary, a delay of 1 year would have simply meant a loss of opportunities, given that SMC conference is scheduled on a 1-year basis. So what to do? Well, make it double. So in agreement with the SMC steering committee, this year we are presenting a virtualized conference hosted mostly on this YouTube channel and mostly, even if not only, devoted to scientific work. And we hope to see you all in 2021 here in Torino for the physical conference, with the summer school and sure with the live concert program and a new call for papers. In this way, we, as SMC community, will not lose our conference, while we, as organizers, will not lose the opportunity to have you all here in Torino. Torino 2020 should have been a joint conference, including the CIM, which is the Colloquium of Musical Informatics, the meeting of the Italian Association AIMI. As the CIM is scheduled every 2 years, while discussing with the AIMI board, we decided to postpone it to 2021, that is, to SMC CIM 2021. Did we learn something, anything from COVID-19? Well, in terms of scientific practice, we have all been forced to embrace online work. At least we became more acquainted and competent with these kind of resources. So, while moving the SMC conference to the internet, we thought that we could try to exploit some possibilities provided by this technological shift that we have been forced to. So, why keep the conference access reserved to a closed group, the registered participants? So we thought that while this is in some sense mandatory for a physical conference, mostly because of budget issues, this might not be necessary if we were online. Thus, this 2020 edition is open to everybody with an internet connection. We tried to devise a way to ensure a certain robustness in content providing, while still providing a certain degree of interactivity. So, as you will see during the conference, we will have video presentations of the works, with a final video chat session in which we will collect questions and observation coming from the audience via YouTube comments. For what concerns posters, we will have open Skype sessions so that anybody interested in discussing a poster presentation would be able to join, and we will have 3 keynote speakers, thanks, that have accepted our invitation, even if in this video format, which is a bit peculiar for a keynote speech. Finally, we wanted to present a music program. So we will have 3 contributions, kindly provided by musicians that we will invite again next year for live concerts. And in order to recognize the work of composers and musicians that have submitted their music for the music calls, at least we will stream in a concert-like format the electroacoustic pieces. The works for the other music calls will not be lost, as we will open the calls again for the 2021 edition. So, it is time that we start our conference. So, welcome to the Sound and Music Computing Conference 2020. And before passing the mic to Simone Espagnol for some updates on scientific works, well, let me say this line that I always wanted to say: stay tuned.
Good morning, good afternoon, or good evening to all of you around the world. I am Simone Espagnol, and in this presentation I would like to give you some guidelines, facts, and stats about this year's conference. I have been in charge of both organizing SMC 2020, following its conversion into a virtual conference, and of chairing this year's scientific committee, together with my colleague Haris Saitis from Queen Mary University of London. While we would have really liked to take this picture in Torino during these nice summer days, unfortunately all we could do is create this bad Photoshop, but hey, we hope we'll be able to take this picture for real next year. This edition's scientific committee included 18 members whose names are in this slide, who greatly helped us throughout the whole review process by taking care of writing meta reviews, suggesting final decisions, and checking the camera-ready papers. So a big thank you goes to them. In our call for papers, we welcomed oral and poster presentations. We were also supposed to have a call for demos, but due to the pandemic and the shift to a virtual conference, we decided to postpone the call for demos to next year. While we received a total number of 110 submissions, unfortunately, not all submissions went to the peer review stage because some were incomplete and others were withdrawn at a later stage. So we were left with a final number of 97 submissions, which, funnily enough, is the same number of submissions to last year's edition in Malaga, Spain. Here you can see the distribution of submissions by country, where papers authored by researchers based in different countries contribute a proportional fraction of 1 to this total number. As we expected, the majority of submissions came from European countries, but we also had submissions from extra-European countries, most notably the US, Japan, and Brazil. In the end, 5 continents are represented in this SMC 2020 edition. Now, a few facts about the peer review process. First of all, we had the help of 110 independent reviewers who collectively submitted a total number of 296 reviews. This means that all papers had 3 reviews at least, and a few papers also had a 4th review. Afterwards, scores and reviews for each single paper have been processed by a scientific committee member who wrote a final meta-review summing up the main points of the individual reviews and gave a recommendation for either acceptance or rejection. Here are the names of our reviewers, whom I would like to heartily thank for the effort and commitment to deliver high-quality reviews, especially considering the particular situation we all found ourselves in. The results of the peer review process are the following. 52 papers were directly accepted, either as oral or poster presentation. 31 papers were directly rejected, and here is this year's novelty, we decided to conditionally accept 14 borderline papers, meaning that the paper would have been accepted only in the case where the scientific committee found that sufficient changes had been incorporated in the camera-ready version. Like in last year's edition, however, changes were actually required for all papers, and the scientific committee thoroughly verified that all authors had taken care of addressing the reviewers' recommendations. This 2-stage review process could ensure a high-quality standard for our proceedings. We had 65 finally accepted papers with an acceptance rate of 67%. Now, a few words about turning SMC 2020 into a virtual conference. As Andrea mentioned in his presentation, we tried to ensure a certain robustness in our content while providing a certain degree of interactivity. Therefore, while on one hand, all our presentations are pre-recorded, on the other hand, interactions will be live. The general public will have the possibility to interact with the presenters via YouTube comments or Skype, as I will shortly detail. We chose these 2 virtual venues, YouTube and Skype, because they are easily accessible and open to anyone, with no need for registration to our conference. We also decided to make all the pre-recorded SMC content available on demand on this channel after the conference concludes. Finally, we have opted for a format as close as possible to the physical SMC, with a distinction between oral and poster presentations that will work as follows. We will have 10 thematic sessions featuring 3 to 4 oral contributions each, divided in 2 parts. Part 1 will be a playlist of video presentations, and Part 2 will be a live Skype Q&A video chat between the session chair and all the presenters. Here's where the session chair will select a number of questions coming from the audience, so we encourage anyone who wants to ask questions to presenters to type their questions in the YouTube chat here on the right side. Please note that in order to type questions, a Google account is required. Keynotes will have a very similar format, meaning that a video presentation will be followed by a Skype video chat with the keynote and session chair. 3 poster sessions will have a different structure. Part 1 will be a poster craze, that is a playlist of very short video teasers, and Part 2 will be a Skype video chat where all interested participants will have the chance to directly interact with the presenter after joining one of the 10 or 11 parallel poster rooms. Direct links to these Skype chat rooms will be listed in the SMC webpage under the Virtual Venues tab, so we encourage all participants to check our webpage at the beginning of each poster session. As you might have noticed, the SMC 2020 scientific program has a variable time schedule from day to day. We decided to have this special format because we wanted to encourage participation from outside Europe as easily as possible and, of course, as much as possible. Therefore, day 1 has a schedule that we believe is friendly enough to our American followers. Day 2 has a more of an European look, while day 3 should be more accessible to our followers from the far eastern side of the world. Finally, here is a general SMC 2020 program. You can find the final detailed program on the SMC webpage, where oral sessions are in green, poster sessions are in orange, keynotes in red, and the music program, carefully crafted by our colleagues from the Conservatory of Torino, in purple. This concludes my presentation. We wish you a great SMC 2020, and we hope to see many of you online.
Okay, good morning, or whatever the time is in your local time zone, and welcome to this video presentation for the SMC conference. I'm Davide, and together with my colleagues from the University of Milan and the Aalborg University in Copenhagen, we're here to present our work that aims at looking into the history and trends of the SMC conference and community. So what we want to do here is to perform a bibliomedical study on the SMC conference proceedings in order to help us reflect on a larger scale on the status of the SMC community at large. In order to be able to do that, we built a tool that allows us to analyze the SMC conference proceedings in order to look into trends. For example, the authorships, for example, the topics that are presented in the contributions, the number of contributions, the geographic distribution, etc. This tool is available online. You have the link in the deck of slides, and so you are free. Actually, you will be encouraged to have a look at the data presented there. Throughout the rest of this presentation, we also are going to have some video segments that will show you how the system looks like. So, a bit of the history of the SMC conference, and before that, the entire field. Now, Sound Music Computing is an expression that has been introduced for the first time during the first half of the 90s. But it was until the beginning of 2000, in particular 2001 to 2004, that the SMC became a conference and later on an entire community. The SMC conference was born as a joint initiative between the National Association for Music Informatics, Computer Music. So far, I see here that we had editions of this conference only in Europe. Maybe one day we will cross the ocean and will reach other continents, even if the participation to our conference, we'll see, already reached the entire planet. So SMC for us is a conference, it's a summer school, is a community, and all in all is an entire field defined by the ACM classification. So our first goal was to organize in a systematic way all the proceedings. Now, the conference proceedings are already freely available. They are protected by Creative Commons license, and they are uploaded on a platform called Zenodo. Now, one of the problems that we have with this platform is that it's not easily searchable, and it does not contain all the data that we would like to have. So our solution to this problem was to build a custom database that is not aimed at replacing Zenodo as an archive of proceeding, but is actually paired with the Zenodo archive in order to track all the information that are not really available in Zenodo. If you ever try to perform a search in Zenodo, normally two things happen. Either you find exactly the thing that you're looking for, or the database returns the complete set of 272 something thousands papers that are stored on the platform. There is not really a good level of flexibility. So what we want to store in our database was to emphasize the variation in affiliation, for example, for authors. Their career evolves, so they move from one place to the other. So we want to have the author as a central information that is maintained in our database. We also want to keep track of the affiliations, the research centers. This actually pose a number of questions, a number of problems on what is defined as the primary affiliation. So we used the conference proceedings and the Zenodo archive as the data baseline to validate the data we automatically extracted. Also, we enriched the database with data that is not available anywhere else. For example, try to infer the gender of the authors of the papers. These in order to try to have an idea of what is the gender gap in our subdiscipline. Just to have a quick look at SMC and the growth of the size of the conference and the acceptance rate. Now, we have extrapolated here this table that you can also find in a paper, and with more data you can find online, just to show the total number of presentations as they grow throughout the years. At a certain point, with a notable exception of 2014, because that was a joint conference with SMC, we kind of reached a plateauing situation that placed us around 100 contributions per year. A bit more interesting also to have a look at the authorship. So who are the authors of the paper at the SMC conference? So in this table, again, we summarized the evolution of the number of unique authors per conference. And again, we have the 2014 edition that is quite different in size because of the fact that it's joined with the SMC. Also interesting is to track how many authors contribute to more than a single paper in every edition, so the ones that are really like the pillars of our community. Also, it's interesting to have a look at the number of papers that spots a certain number of authors, and we can see that empirically these curves follow the so-called Lotka's law, where the number of authors making X contribution is 1 over X to the power of A of those making a single contribution with A that is experimentally validated to be close to 2. Also, we can see here the overall, over the all editions of the SMC conference, the number of authors with a certain number of papers, and we have a vast majority of contributors that contributed only one paper, and then we have a smaller number of authors that are what we call recurring authors that contribute with more than one paper. So if we look at the composition of the research groups in our field, we can see here that each paper is authored on average by 1.4 institutions. So there is collaboration between different research centers, between different universities. The number of papers with a certain number of authors per edition is mostly concentrated with 1, 2, or 3 papers. It's rare to find authors with more than 3 papers per a single edition. Okay, just to make some, if you allow me to use this metaphor, high fidelity, a list of top 10s, we have top 10 recurring authors, so the one that contributed the most to in terms of the number of papers that presented to the conference. The one that established what we consider a large collaboration network, so the number of unique co-authors that they work with during the time that they spent at the SMC conference, and the number of authors that participate in the most conferences. Now, we have nobody that attended and presented a paper to all the conference, but we have a number of authors that approximate, that are getting close to that number. Also, we want to have a look at the number of countries that are represented by the SMC conference, and in particular, we already have 51 countries spanning over 5 different continents, so we basically reached everywhere in the world, and 585 unique institutions that include universities, research institutions, music institutions, in particular conservatories, research centers, and private company. Even if then that on average, 90% of the contributions come from universities or university-like institutions. Okay, this slide is a bit dense, is just to show you that we have the possibility to track the what we call connectivity graphs between authors and institutions. Now, a bit more of that you will be able to see for yourself in the interactive presentation, or if you will decide to use our application. So you can basically check if there is a connection in terms of authorship between 2 individuals or 2 institutions. And again, we can see here a sort of clustering effects around some of the pillars of the community in terms of authors that contributed a huge number of papers and interact with many different authors. We kind of established a link with many other different research centers or authors, as well for the research institutions that are, let's say again, at the center of our research, established collaborations, established networks with other research centers. Now, after focusing on the authors, we're going to look at the topics presented in our conference. Because one of the missions of SMC when the field was established was to basically promote a certain set of topics that are the one identified in, for example, the European project Sound to Sense, Sense to Sound. And in order to be able to do that, we analyzed the titles and the abstracts of all the articles that we have. This information is available online. Again, by having a look at a single term, we cannot really make many inferences. A bit more interesting is to have a look at digrams, collection of 2 words, as they appear in titles and abstract. And in particular, here we can see some interesting trends. So the decrease of the synthesis, this is the root of our terms, and analysis over time, probably because we reach a plateau. We assume that we reach a plateau or a certain maturity in the field. Also paired with the increase of the term design, the active intuited from the Sound to Sense initiative, or the user and experience intuited from the taken from the human-computer interaction field, and in the last couple of years, the rise of machine learning and increase of features extraction. So, to jump to the conclusion of our work here, we saw that the participation widened over the years in terms of unique authors, in terms of institution, in terms of countries, meaning that there is interest around the SMC community. Also, the female authorship increased and peaked in 2019. Well, we can say what will happen during this year. The average number of authors per paper increased. The degree of connectivity of unique authors and institutions increased over time, meaning that we are actually building a research community that is increasing the level of collaboration between institutions and projects. So what can we aim for the future? Now, the acceptance rate, even if it's not the only perfect metric to tell us how good or bad a conference is far from other comparable top-tier computer science conferences, even the one in the field of computer music. So what can be done? Should we try to get a more narrow focus, for example, like it happens in NIME or ISMIR or DAFS, or we do not really care, we believe that we are going in the right direction by keeping this very broad definition of what SMC is and what can contribute to SMC. by building our database, we realized that there are things that we can really do in order to improve the quality of the data. For example, we propose to change the LaTeX template in order to provide a standardized way to input the authors and institutions. Keep an explicit mapping between authors that have multiple affiliation. This is quite difficult because by not having any form of structure in the LaTeX template, different authors decide to present their multiple affiliations in different ways. Maybe even during the same conference, they appear in different papers with the same multiple affiliations presented in a different way. We can, for example, think about having a structured, extended information for authors, for example, by linking each and every author to an external platform, such as ORCID. For example, this is becoming quite a common requirements for certain publication. I'm thinking about science. Another thing that we realized is that we do not actually currently support non-Latin alphabets, meaning that we force authors whose name is not written in a Latin alphabet to perform a transliteration with all the problems that come from this. For example, the non-uniqueness of a transliteration. So we have, over the course of the year, certain authors that decide to transliterate their name in different ways, making it very difficult to track them down. Also, in order to make the process of extraction of this information automatic, we encourage the idea of submitting the original source file as well as the final document for the submission. And maybe we can start creating a custom set of tags, so a syntax and a semantic for authors and institution. So what we would like to see happening in the SMC community now. So the first thing that we want is to encourage everyone to have a look at the website that we built and report any discrepancy in the data. We are not perfect. I'm sure there are plenty of mistakes in the current database. If we adopt a crowdsourced approach, we can easily fix that in relatively little time. And so considering the little overhead that comes from this system, we would really like to see future editions of the SMC conference to adopt this system and so populate the new edition of the SMC conference every year, not only on Zenodo, but also on this platform. Okay, thank you very much for being here, this remote here, for this presentation. I am available live, I think, for questions, and I hope to see you next year, wherever the SMC conference will be. Thank you for listening.
Hello, people of the internet, and welcome to this neon-colored extravaganza that will guide you through the worst corners of the back library. My name is Daniele Ghisi, and I will be presenting this, let's say, work, which I did with my colleague and friend, Andrea Agostini. Forgive the tone and the graphics of the presentation. The lockdown has been hard on us, and intense photoshopping with bright colors seems as good an activity as any. Bach is a library for computer-aided composition in Max. Andrea and I started developing it around 2010, and the underlying principle was that a real-time paradigm could be a game-changer to handle scores as interactively as one could handle audio buffers. We think we had luck to take a couple of right decisions at the very beginning, but in retrospect, we made some really poor choices, and we would like to come clean today on the mistakes we think we have made, and on how we have tried to solve them, in the hope that someone else may benefit from our occasional shipwreck, and in the hope that brighter minds than ours may come up with elegant solutions we hadn't thought of. Consider this as a sort of step 1 of AA. In the grand tradition of BuzzFeed posts, we'll present to you the 10 worst mistakes, 10 ways in which things have gone wrong. Of course, actual mistakes are much more than 10. I'm sure that both I and Andrea have our own personal shame lists, but this list is our intersection, the 10 worst mistakes we both agree upon. The conference article contains more ideas about, perhaps not ideas, let's say details. Perhaps not even details, let's say sentences. The article contains more sentences than this talk. And also, it strikes a marginally more serious note. But there is a point, I think, in self-deprecating humor. We know that Bach's user base is growing large, and it seems important today, as Bach turns 10, and as we go open source with it, to put a spotlight on its shortcomings, and not just on its strong points. Let's start with mistake number 10. 2 editors are one too many. When we started Bach, we were both intensive users of open music, and it made sense at the time to quote-unquote borrow some of its paradigms. One of them was the opposition between metric and proportional notation. That is why in Bach we have 2 score editors, the first one dedicated to proportional notation, Bach.roll, and the second one dedicated to traditional metric notation, Bach.score. In retrospect, it would have been better to think of a single editor, combining the 2 behaviors. It may have led to more interesting scenarios. And if you think that I'm using the combined editor right now, well, unfortunately, it's just a picture with a roll and score superposed, so sorry about that. We have done a couple of things to ease the pain. The most important one is probably the possibility to warp the time grid of Bach.roll in a very general way, including the ability of matching it to the spacing of a Bach.score. Vice versa, we have added a proportional notation display for Bach.score, with a few small tricks to make it easier to read, but having a single object would have been more powerful. Mistake number 9, 6 inlets are 5 too many. Another thing we have quote-unquote borrowed from open music is the idea of having separate inlets and outlets for each of the main musical parameters. And yet, the more I use computer-aided composition, the more this paradigm where one builds each parameter separately and then they are somehow magically combined to form a score, well, to me it feels like an old gizmo from the 40s or something. I tend to avoid it whenever I can, and when I see patches like these, I have an urge to scratch myself and blow the dust off. Scripting feels much more intuitive and practical in a way, and Bach somehow has evolved to account for it much more than for separate parameter handling. In any case, all the information about the score is output from the first outlet, so we could have devised a couple of helper tools to set and get separate parameters from there. Mistake number 8. Queries are slow. Bach's lists are fast, but they only can contain up to a few thousand elements. The issue is how to deal with 10, 100, 1,000 times more elements, which is not that uncommon. Bach implements its own data structure called Lisp-like linked list, or LLL for short, which is used to communicate across all the library. LLLs are lists that support nesting and have no hard limit in size or in depth. But this doesn't mean that searching through them is going to be fast. As a matter of fact, it is bound to be ON, which means linear in the number of elements, and hence relatively slow for large lists. To account for this problem, we have created in the data library a set of objects to deal with SQL databases. Granted, filling a database will still require more time, but once you've done it, your queries will be sublinear. Mistake number 7, not enough numbers, and more specifically, not enough integer numbers. And this is not a Bach issue per se. It is very easy to have max overflow. Look at this product of primes yielding a negative number. But this is not a good thing if your representation system relies on rational numbers like rational duration in music. And think about this, whenever you put 2 durations together, there's actually a computation involving the least common multiple of their denominators somewhere in the code. Look at how clumsy it gets when we add durations whose denominators are successive primes. And look at how Bach completely messes things up at the overflow point. It doesn't have to be like this. One of the things we miss the most from Lisp is its arbitrary precision arithmetics. The same algorithm in Open Music yields an ugly to see but yet very consistent result. You can just keep working with exotic fractions and then rely on some future quantization. This is not possible in Bach. If you need to work this way, Bach roll is the only way to go. I think that at some point in the future we may want to integrate an arbitrary precision arithmetic library that comes into play for large numbers only. I would love to see something like this in Max at some point. This is a test for primality of a Mersenne number, and by the way, no, that's not a working implementation, that's just an image, sorry about that. Mistake number 6. Bad pitches. We have got accustomed to the idea that in computer-aided composition a pitch is represented by its value in MIDI cents or in MIDI numbers. And don't get me wrong, I love cents and MIDI numbers as much as the next guy, but a pitch is a more complex entity. Just have a look at this chord and tell me if it doesn't make you wanna cry. In older versions of Bach, we handled enharmonicity in such a cumbersome way that I'm ashamed of even talking about it. But now we are relatively proud of our solution, which is a new data type called pitch, which one can express in a variety of ways. For most purposes, pitches behave like sort of numbers. You can make some arithmetics with them. Importantly, a pitch is also an interval, and an interval is also a pitch. Exactly like 100 cents represents both a very low C sharp and a semitone, D sharp 0 represents both a very low D sharp and an interval of augmented second. This is crucial to make arithmetics with these guys. Here's an example of how things get transposed, by augmented seconds or by minor thirds. And here's how you may want to generate a circle of fifths via an arithmetic series. And yes, middle C is C5, that's not up for debate. Mistake number 5. Escaping is hell. Look at these symbols. It contains parentheses which Bach interprets as a sublist, which is fair enough. But then we need a way to tell Bach that this was supposed to be just a symbol. We have decided to go with backticks as escaping sign, so you put a backtick before anything and it's going to be interpreted literally as a symbol, not parsed into any other thing. We were relatively proud of the backtick because it was ASCII and it wasn't that much used. The way we implemented it, it only escapes the portion before the first space, which means that you don't need an ending sign for escaping, so we thought it was cool. In our defense, we would have gone with the double quotes, but in Max there's no way to use them consistently for symbols that do not contain a space within them. The real issue with backticking came when we put Bach.eval into play. Bach.eval implements a scripting language for Bach. And at some point, we really wanted to use symbols as keys to retrieve values and set values. And at that point, things became very, very difficult to handle. The only way we could do that with the escaping we had was to put a lot of spaces pretty much everywhere. It was a mess. The way we solved it, at least within Bach.eval, is by using single quotes in a Python style, let's say. But this only works for Bach.eval. I find it very clean, but unfortunately it's only for Bach.eval, because otherwise it would have broken the compatibility of older patches, so we didn't feel at ease with that. And yet some nights when it is cold outside and I crawl into my warm bed with a chocolate chip cookie and a cup of herbal tea, I dream of this. Mistake number 4. Bad names. Classic mistake, always in fashion. I think our worst naming was probably Bach.append. Many Bach modules mirror for Bach lists what ZL modules do for standard Max lists. But the issue is that Bach.append did what ZL join did, which is quirky. And then at some point, you want a module that does for Bach lists what append does for Max lists. And you run into trouble, you cannot use append any longer. It takes 1 minute to choose a bad name, it takes 10 years to try to let it go, and there's still not enough. We deprecated Bach.append at some point, we added Bach.join, but we had to use the awfully named Bach.postpend as a proxy for the append module. Mistake number 3. Very much related. Bad defaults. No one in the history of computer music has ever needed to iterate a list for more than one level at a time. I may be exaggerating a little bit to make a point, but bug.iter and bug.mapelement both operate by default at all levels of depth, which is essentially what you never need. And this obliges you always to write a max depth attribute explicitly. I think that for this one we have a plan. We will introduce two more modules, bug.for and bug.map, that we do the same things at one level only. But the jungle of default is full of ramifications. There's certainly no lack of bad default choices in Bach. We chose the direction of rotation for the lists wrong. We chose different depth default for different modules, which makes sense, I think, individually, but it doesn't make sense in general. And we get to mistake number 2, too complex abstractions. I think that a patch is worth 1,000 words. Meet Bach.counter. Meet Cage.fm. The thing is, we all love Max Visual Programming, but it easily leads to spaghetti coding, even for relatively simple patches. And this makes those patches hard to read and hard to maintain. Our tentative solution is to introduce a scripting language called Bell. And yes, it is another scripting language, but it makes sense, I think, because it's really tailored on Bach lists. Although I suppose that every new scripting language could make this argument to some extent. But honestly, from my own experience, I've been really using it more and more because it helps streamlining complex patches and it reduces the complexity in one point. And it makes it also more maintainable. Sometimes you really can do in a couple of lines of code what you may need a complex patch to accomplish. We have already started to modify some of our own abstractions to account for it. And speaking of coding, let's get to mistake number 1. Drum roll, please. Bad coding. Now that Bach is open source, you can go and have a look for yourself. The code is awful. Okay, mostly awful. There are perhaps portions of it of which we are relatively proud, but they are drowning in a froth of dusty layers. The thing is, we learn how to code properly. Well, we try to learn how to code properly while writing Bach. And the older the code is, the higher the chances that it contains weird naming conventions, unnecessarily long loops, and so on. Plus, we started using the CMax API, and we honestly wished we had used more C++ at the beginning, because it would have made life easier for many purposes. And yet, in spite of everything I've said, we love Bach no matter what, and if everything goes well, we shall spend the next 10 years trying again,
failing again,
and we promise our Cahiers de Doléances will be much longer in 2030. Peace and love.
This paper discusses recent uses of Bach Automated Composer's Helper, a Max library for algorithmic composition. As the title states, this is a user's perspective, so it is only showing one particular aspect of what you can do with Bach. To situate the domain, it best falls under the category of technology for notation and representation, tenor, like the conference of the same name. And of course Bach more specifically, due to its strong Lisp influence, situates itself within the tradition of CAC, computer-aided composition, as a potential successor to softwares like Patchwork, OpenMusic, and PWGL. I will divide my talk in two parts. The first part deals with the new Bach.eval object, Bach Evaluation Language for LLLL, followed by a few examples of code and their application on choral music. I will then present the current state of my ongoing artistic research in the instrumental domain, linking with Quentin in particular. So the first point in this presentation consists in discussing the max paradigm for computer-aided composition when dealing with symbolic notation. I highly recommend to read the author's articles relating to the topic, but I will exemplify in my own practice some of the problems addressed in those papers, as I believe it exemplifies what's explained on a more theoretical level. To do so, we need to recall that in Bach, the data structure called LLLL consists of nested lists in a manner inspired by traditional computer-aided composition softwares. These lists can be represented as tree. Each time you go further down the tree, you add a level of parentheses. At the bottom right of the tree, so with already 4 levels of parentheses, you can see the slot content, which is what composers interested in the playback possibilities of Bach often find of interest. In our view, slots give Bach great advantages over softwares like Patchwork, OpenMusic, or PWGL, in which most of the formalization processes were concerned with the organization of pitch and rhythm. Indeed, the slot mechanism in Bach allows to store within each note a large amount of metadata, which can then be mapped to anything in order to retrieve, for instance, automation curves during playback. Here you have an example of a vocal synth, but slots are very versatile and will later show a very different approach with instruments. So, as we saw in Bach, one way of composing may consist in adding add chord messages with onset, pitch, duration, velocity, and with all the necessary information stored as slot content. For instance, with voices, those can be phonemes, text, dynamics, and for instruments, the path of which sample to play, which note head to display on the score, etc. This is a situation where the real-time data flow max paradigm makes things a bit complicated when we need to add parentheses one by one. This new way of formatting messages makes it a lot easier to build this composer UI, which generates microtonal polyphony. If we look back at the 16th century polyphony, more than harmony register or any other means, contrasts were mainly achieved through alternations between homorhythmic and imitative passages. And this is what this patch is about. Are they singing together? Do they start together? Do they sing at the same speed? Etc. This new ability to write few lines of code and manipulate variables in Bach also makes it a lot easier to automate tasks. I will now show a queuing system for part extraction, allowing for the singer to hear what comes next, turn the page at the right time, etc. The queuing system referred to in the article consists of recalling the performer with his next phrase, so that she feels comfortable with text as well as intonation. Let's now see how to automate that. So here all the variables are capitalized. By iterating on each voice of the score and comparing each note 2 by 2, we're trying to identify the distance between one note and the following. So onset 1 is the onset value for the first note. Durée 1 for duration of the first note. So final 1 equals onset 1 plus durée 1 or duration 1. So here the distance named écart 1 and displayed in yellow is small, because the difference between onset 2 and final 1 is small. On the other hand, in that example, final 1 and onset 2 are further away from each other. So écart 1 is larger, however still too short to sneak in a cue for the singer. Here, on the other hand, there's plenty of time, so the cue needs to start as late as possible. Start minus dur equals start minus n minus start equals 2 start minus n equals 46 seconds. When the pause is short, the cue needs to be provided as soon as possible. so just after the previous singer's phrase. So here is how it's implemented in BEL, short for Bach Evaluation Language for LLLL. If we have enough time to anticipate, then we paste the cue just before the next phrase. If, on the other hand, the singer has only a short rest, we pass the cue as soon as the previous phrase finishes. Similar methods are applied to page turns. With animated notation in particular, one has to make sure the page turn doesn't occur in the middle of the phrase, and so on. So now to give a quick overview of what I do with it, well, we just saw the very tonal Vedi trompetea passage. In general, however, the harmony is more driven by spectral techniques than that. In this particular piece, sounds were synthesized in MUX, a VR interface, which, among other advantages, makes gesture to sound mapping really easy. So MUX oscillators were then recorded in order to analyze their pitch content, on the top of which I then built the polyphony. In Common Ground, similarly, the polyphony is built on the top of synthesized sounds, realized with the synthesis toolkit, RAS, Blowtar, and the like, via Percolate in Max, or with FFT filtered FM spectra, like in this example. You'll notice the choreography is realized in score using the spat notation of Bach slots. You've also noticed the HMDs for singers, which is something I started doing last year in the piece Mit allen Augen, publishing the results at NIME and Tenor 2019. I believe it opens doors to interesting situations in performance. Technically, all the scores are synchronized by Smartvox, whose Tenor 2017 remains the main reference. It is a form of NMP, Network Music Performance, synchronizing all the scores through the browser, and as stated in Tenor 2018, audiovisual scores and parts synchronized over the web. It works on the web, as you can see in this demo. However, I believe it remains important for me that the performers are located in the same room. So we are on the local Wi-Fi here, rather than the internet. For the second part of my talk, I would like to focus on instrumental writing and the linkage with the Contimbre library in particular. The starting point consists in recalling that a computer-aided composition patch yielding a score with only pitch and rhythm will be of little use, say, to a German post-Lachenmann composer who would like to formalize instrumental techniques. I therefore built a sort of dictionary with each playing technique and its corresponding symbolic display for each instrument. Here is an example of the sub-batch generating the flute part. Again, the few lines of code written in bar.eval at the bottom help making it more synthetic, with less spaghetti-like cables and the priority issues they may generate. I've then built a machine inspired by the real-time generation of the cage.not random object, with the ability to dynamically control tessitura, dynamics, density, playing techniques, etc. I have here a machine which generates instrumental music according to a list of 11 parameters scaled between 0 and 1. The first step consisted in saving some presets according to my taste in order to build a small dataset. Each of these points or presets corresponds to a type of instrumental writing tied together with a harmony. Here the ones on the top are in the high register and the ones on the left have longer duration. The goal is to interpolate between closed presets. For instance, here 2 points have both low dynamics and high register. So register or tessitura is constant, high, as well as dynamics, low. And here the music will go slower and slower. You notice towards the end a harmonic shift as well as a change in instrumental writing, more notes at the flute. The ML library features an object called KD-tree, which, given a configuration of parameters, will return the closest preset in my dataset. Again, in order to interpolate between two closed states. The most salient features are that the second state has lower dynamics, and it is a bit slower. The harmony changes each time the red line crosses the orange one. This one is pretty self-explanatory, going from low to high register, forte to pianissimo, and ritardando. In those two last examples, although harmony is still very important, the gradual changes of playing techniques, texture, and register seem even more directly perceivable. I hope I've shown in this presentation how Bach and its new features can be used to model composer and performer-oriented audiovisual scores, both in the vocal and instrumental domains. With the rise of AI, I would like to conclude with a question I currently address myself. Most of the results in this talk emerge from explicitly programmed procedures. So I am now trying to give more autonomy to the system. Distance calculation with objects like data.distance, ml.kd-tree or mubu.knn gave significant results. I've shown how preset interpolation can be modeled as a gesture with Mubu. Since a plethora of machine learning tools today are able to recognize gestures, I wonder, for instance, if mubu.xmm or Wekinator could be used to create new gestures instead. Thank you for your attention. Please ask questions.
Okay, so here we are, and first of all, even if it's not related to this session, let me say again thanks to everybody participants, authors, keynote speaker, and musician for joining us in this new effort on this virtual SMC. We call this this beginning session anniversary because, of course, it deals with our community in the first paper, and it deals with also the anniversary of a project which has encountered a lot of success. And I think it is important to think back about what we have done as a community and in relation to our single project, something that typically it is many times overlooked, no, while looking for new things. So I saw, by the way, that there has been a strong interaction in the chat. This is good. This was not, how can I say, thought before, but I think it is an emergent issue. So we are happy of it. I will collect some impression and I will propose some questions, let's say, emerging from what has been said in the chat. So first of all, I'd like to ask Davide concerning the history of SMC. We saw that there's been you made a strong effort in trying to organize, to discuss the history of our community. I was just thinking if we can say something about the relations between our community and other communities, in the sense that, of course, you have worked on the papers and the conferences, but I was asking myself if it could be interesting also to think about the relation between SMC as a community and other communities, maybe not necessarily the one more related to us, such as DFX or NIME. Maybe we spoke about human-computer interaction. So what is the relation between SMC and other human-computer interaction communities? So maybe, I don't know if you can say something about this, if you think this is an interesting project concerning how to map our activity.
Okay, I hope you can hear me. I don't know if...
I think so, actually. At least on Skype, we're hearing you.
I don't know if the video will switch or just the sound will switch. Anyway, this first question that you asked is very important for the community in the sense of how do we place ourselves with respect to the others. Now, we mentioned some of the closest communities to us, NIME, DAFX, and ISMIR. And we know from our personal experience, most of us as authors contributed to one or more than one of these communities. Regarding the communities that are a bit more far from where we are right now, I still think there is a certain amount of overlap. Of course, there always is, but also a room for possible interaction. I think that one of the nicest places where these kind of overlap happened in a sister community is between ISMIR and their conference of machine learning, NIPS. They managed to start a joint project. I think it was Oriol Nieto that is working at Pandora. They managed to get first a special session within that conference that then expanded to a more regular, I don't know if I can call it a feature in that conference. Pursuing a joint conference between the SMC and other communities would be for sure, I would say, interesting at least, if not very fruitful, because we're at a point in time, I personally believe in history, where the best results that we can get happen when we bridge together different communities, different people that think about different things. I just now realized how Italian I am by how much I move in my hands. I hope this is not distracting. So I hope you followed my point here, more or less.
Okay, thank you. I have a second question, this time for Daniele and Andrea Agostini, who has joined us, and the two. So we have the two responsible for the back project. So it seems to me that the Bell language share, in some sense, the same, let's say, trend of Gen, as far as I know. It means that sometimes it's easier to write code than to visual organize things. I was thinking about the idea of open source. So you say the project now is open source, and you wrote also this Bell language. Thinking about pure data, which is the main, in some sense, possible target in relation to Bach. As far as I know, they are strongly connected to Python from this point of view. So I was thinking if you have thought about using, I think you mentioned it, using an existing language such as Python, which is widely used, and maybe this could help the porting of the project to other system. And also, speaking about open sources, when you open source a project, you hope not only to have more users, but mostly to have more developers. So I was curious about the success in these terms, which is relevant to create a community around your project, no?
Okay, who goes?
I don't know who wants to
You go.
Okay, I go about Bell and then you go about the community. Okay.
Oh, come on,
So,
you get the easy one.
okay, but anyway.
Please, be quiet.
Yes, of course, we considered, the first thing we considered was basing our quest for a textual language upon an existing one. Actually, the first and more, so to speak, obvious choice would have been Lisp. Python was sort of a second choice, and we considered it all, of course. The real problem is that we needed to work upon LLLs, and LLLs are quite an idiosyncratic data structure, and so it didn't really fit well with any of those programming paradigms. So it was either we chose an established language and somehow we hack it and we find some convoluted ways to work with LLLs from within it, or we choose to stay as close as possible as to the LLL architecture, but we need a language which, of course, is not completely exotic. It's also a pretty simple language, and I think that anyone who knows how to code in Python or Lisp, because the Bell language has sort of a double. It has a sort of double paradigm, both imperative and functional. So whoever is familiar with either of those kinds of languages should grasp Bell very, very quickly. So then there is a lot of articulation about this subject in the papers that Jonathan Bell quoted in his own presentation. So I'll forward you to them if you want more details about this. Daniele, open source.
Oh, come on. Let me just add also that we have tried to make, Andrea has tried to make Bach.eval as compatible as possible with Bach.exp and then exp, which is another reason, I think, for being as Maxian as possible, even if that means a bit farther from Python. Community, yeah, I'd love, the short answer is I'd love to see someone taking up the project to branch it and make a pure data version of Bach. But it's a huge task because, as we said repeatedly, the code is not well written, and I'm not. I really hope someone will contribute to many extent, because there are a lot of things that could be done, and we are just two. On the other hand, I don't know. I wouldn't know if I'm optimistic or pessimistic, because if it were me, I know it would be a huge task, because it's a huge project with a lot of lines of code, thousands and hundreds of thousands of lines of code. I would feel intimidated. So I would probably start small, adding little things, and then maybe taking over a larger project. But again, that's just me. I hope that someone at some point says, you know what, I will make a branch for pure data, and I'll keep it
I was
alive.
also thinking about someone joining you in developing Bach in Max. I mean, not necessarily joining you to port it, because I know that Bach has been used is the base for other projects such as Orchidea by Carmine Cella. So I was just thinking about the possible base of the developers actually. Okay, I think I have to skip. I'm sorry, Daniele. I have to
No problem.
skip to Jonathan because of scheduling, so we don't start too late. And Jonathan, you showed us a project, which is a set of projects related to the use of Bach, which is always interesting from, I think, the developer perspective, because typically you develop something, then you have user doing different things, and in particular, if I understood clearly, I can say that we can say that it's a set of projects related to some sort of computer-aided, one can say, of course, composition, but also notation, because these systems are used live to provide cues for performers. I was curious to know if you have thought, and maybe you have, and I haven't understood, if you have thought about creating live the composition, it means the notation for the performance. So rather than queuing an existing score, to generate live this kind of situation.
Sure. Well, I get often this comment. Of course, when you see live generated notation, the first thing you think of is Umberto Eco's Opera Aperta and je sais pas le dire. These kind of open works that generate on the go. But as you said, yeah, it's live. Maybe I think a lot of computer-aided performance, and in a sense, for a singer, what he likes to do is do his own thing on stage, and in a sense, he or she wouldn't like to get something pop up, and she hasn't prepared her breath. And in a way, I've done it a little, but not so much. I would be more interested in perhaps having a conductor able to speed up at certain passages, sort of en test for a way of doing things.
Okay.
Yeah.
Okay, so thanks. Yes, it's a known divide, the one between, in some sense, let's say, musician and improviser. It's not the same thing. They can overlap, but sometimes it's a different kind of attitude, no? So of course it's important to deal with both sides. So I'm looking to the chat right now. I don't see any other questions. We have a couple of minutes. I am here with on Skype, and I have this sort of.
There's a delay with YouTube.
Yeah. There's a delay probably. So maybe Simone, I think we can proceed in our conference. I'd like to thank you all for being here in this unusual setting, and of course to be our test for the first session, which is more complicated, of course, technical. Then we will try to go seamlessly. So thanks to all, and let's see the next session.
Hello, welcome. It's a great honor to give the open keynote of SMC 2020. Thank you very much to the organizers for the invitation. My name is Anna Chambaud and I recently joined the Montfort University. I'm part of the Music Technology and Innovation Institute for Sonic Creativity, where we explore broadly innovative music applications for music technology. And so we specialize in electroacoustic music and sonic art. I would like to start this talk exploring the synergies between sound and music computing and human-computer interaction. So there is this recent publication published at SMC 2020, which looks into 16 years of SMC. This paper is by Mauro et al. And so it explores the different topics that have been covered throughout the years and trends. And it starts defining what sound and music computing is and how it started. I will read it aloud. By choosing this name, the proponents intended to go beyond the term computer music, which was interpreted primarily from a music perspective, and to define a discipline in computer science. If we look into the Association for Computing Machinery classification from 1998, we see how sound and music computing is classified under information interfaces and presentation. And just to clarify, this classification is used for both indexing and retrieval of computing papers and articles. Now in 2012, ACM proposed a new classification where sound and music computing was moved to applied computing and arts and humanities. Back to this Mauro et al. Paper, it is one of the conclusions, SMC is a broad discipline that touches different topics, and this kind of variety then makes it difficult to classify properly or in a taxonomy. So it's just to raise that it's a multidisciplinary field. But moving a little bit up, what is HCI? As a definition, human-computer interaction can be defined as a discipline concerned with the design, evaluation, and implementation of interactive computing systems for human use. And I would like to stress this human use aspect and also the design and evaluation part of the workflow. And also it concerns the study of major phenomena surrounding them. If we look into this other term, computer-supported cooperative work, it refers to the understanding of how computer systems can support group activities. So here we see a matrix that has been borrowed from the computer-supported cooperative work literature and Álvaro Barbosa adapted to musical interfaces and applications, where we see these two dimensions, time and space. That means that activities in group can happen collocated and remote, and synchronous versus asynchronous. So then we can find here 4 scenarios that are possible throughout this collaboration that can happen to be a musical collaboration. So this talk is a personal journey ranging or starting from the creation of music prototypes that I will explain in a minute, then moving to bring in this collaborative participatory layer when building music experiences, and will end to this present time of exploring collaboration and participation, building music ecosystems. So music prototypes. Here you can see a poster that I presented in my first summer school, which happened to be in 2008 in Genoa, and it was the SMC summer school. So it's nice to be back to Italy, even though virtually. And so in this poster I was presenting, the point was to show sketching music as an alternative way of interacting compared to desktop interaction or mouse-driven interaction. And so the idea was to present different prototypes that we were building during this master. So the first prototype, built together with Gerard Roma, is a pen-based interaction prototype where you could draw sound waves on an electronic board. In this case, we could build it on the same laptop using a kind of a handmade or custom low-cost physical light pen that was working with infrared and capture with an infrared camera as well. But basically what you could do here, we could demonstrate that you could draw directly with a pen on the screen. And that was a spectrographic sequencer. A second prototype that was kind of exemplifying this approach of sketching music was the wavetable that we also built with Gerard Roma when we were studying the master. And this started as a course work, and then we continued along, and we presented it during NIME that same year, which happened to be located just right before the SMC summer school. And so this is built using the reactable class approach that I'll explain in a minute. But basically here you could you could have a hands-on sound wave editor where you could edit the wave, or you could draw it and then erase it and modify it and apply effects, but using this tangible interaction. And the third prototype was based on mobile interaction. Here there is a pocket sequencer, which is based on a basic sequencer with a matrix of different sliders that you could modify pitch and volume. This, for my master thesis, turned to be or became a kind of a sampler where you could have 4 tracks and record them on the go and modify the tracks. And in both cases, I was using PDA, which was a version for mobiles of PD. And the main point here was to also explore interaction on the move, on the go, with mobile phones. And so in terms of evaluation or how to assess these prototypes, was very much based on this human-centered design process. And this diagram comes from Don Norman's fantastic book, The Design of Everyday Things, where there is this cycle of idea generation, you then prototype and then give it to users to test, observe the kind of the uses and feedback, and then that informs back to the new cycle of, again, idea generation, prototyping, and so on and so forth. However, it was really an open question how to evaluate these kind of systems and this kind of interaction, which is kind of rich in terms and varied and complex, and to what extent and how it was possible to borrow HCI research methods and what would be the kind of the parameters to look at. These were all open questions. And in a way, you could see it as establishing a bridge between, on the left, the common course book that we had during the master, Human-Computer Interaction, with great readings and papers on formal HCI studies. And on the right, you would have this roadmap for sound and music computing, which was also at the time and understood as like a roadmap, a way of seeing the future, or like how this promising field was going to satisfy the needs of society, and so all the promises. So there was kind of a need to bridge both fields. The good news is that authors such as Bill Buxton explore extensively this bridge and inform theoretically also how music and music interaction can inform HCI. And so he talked about, in this seminal article, Artist and the Art of the Luthier, he mentioned about this, the artist spec, and basically if you could satisfy the artist spec or specification, that means this artistic interaction, all these complexities and gestures, then everything else would be easy. And mention also Sergi Jourdain, who follow up this path, and here you see on the right his PhD work, and this term he coined digital lutherie, which basically refers to those who create digital musical instruments, and in his thesis explored and thoroughly what are the characteristics of these digital musical instruments, but also what shall we keep from acoustic instruments, what should we improve, and also what digital musical instruments and computers are bringing new. And one aspect raised is this collaboration due to this multi-threading that is possible with computers, but also all of a sudden you have numerous parameters, and then sharing those parameters is a way also to divide this complexity. So the reactable, as you may know, was kind of it came part of this research, and it was built at UPF by Jourdain, Geiger, Alonso, and Kaltenbrunner. And basically, yeah, it brings all this notion of what a digital musical instrument is, taking the good from the acoustic instruments, bringing also the good from the digital musical instruments. And well, you see on the right diagram that explains or outlines how this system works. It's based on this tangible interaction where you have objects on a surface to control the data, but also to show or represent the values of the data. And then also behind the scenes, you can see there is a computer vision system that tracks these objects. And then we have different modules for the audio, for the visuals, and so on. And this also, it's another characteristics of DMI about separating control and audio output. But then back to this matrix of computer-supported collaborative music applications, just to mention then that collaboration or collaborative musical applications can be seen as exemplary of digital musical instruments, because basically explore this new potential that DMIs offer. And that's what we will keep exploring in the remaining of the talk. So moving to the second part, and as part of my PhD research, I moved to this exploration of interactive musical tabletops and how to study them. And so the problem space was to study not only the artifact, the tabletop, but also the musicians, which were more than one, so a group, and therefore also the collaboration and the music produced, but also the observers and the audience. And so the open question was how to study this social interaction in this new setting. So two key references for creating this theoretical framework to understand this new phenomena are these two books and authors you see here on the left, Where the Action Is by Paul Dorish, who has coined this term embodied interaction in order to explain this tangible interaction, but also this social interaction and this co-creation of meaning during these hands-on activities. And on the right, Plans on Situated Actions by Lucy Suchman, who is proposing the notion of situated action as a term that refers to the creation of meaning when a particular action is happening with a particular group of actors in a particular moment of time using a particular piece of technology. And so both references help to frame the kind of what I like to term embodied music interaction, where you can see here a diagram of different ways where the body is part of this interaction with the technology, ranging from tangible to mobile interaction to wearable and laptop. And out of the different characteristics, here I would like to highlight the shareability property, which all these DMIs support in a way or in another. So putting all these pieces together, we will see now a few examples of each of these modalities. So first study was the one you will see here with expert musicians and how they were using the reactable over time and what happened. And so the research methods used here was video analysis, which is a common research method in social sciences, but looking into musical tabletops and musical interaction on tabletops. And so through this video analysis and recording all these sessions, we had several findings. One was the beginning of the experience, the groups were misusing the objects, as we've seen in the video, but later on they developed complex techniques, as this preview technique we see here. Another example, still with the reactable, but in the museum. So the idea was also to bring the video recordings there and observe how reactable was used in this informal context. So the kind of interactions would be as the one you see at the bottom left. So we were expecting those, but then after observing or viewing these video recordings, we found out that there was also in-between interactions or in-between group interactions where one group, as you can see here, would leave one patch working. So this is playing actually, and after a while another group came, for instance, and continued the patch, so continued the music. So that's why you can see this as an example of asynchronous co-located collaboration. And so the way also of analyzing or doing research is what we call, or it's called research in the wild. So the idea is that you go in the wild to gather a real world experience. So moving to another example, in this case we move to remote synchronous interaction, and here the idea is to explore EarSketch, which has been developed at Georgia Tech and is a web-based software based on the digital audio workstation metaphor, where students and users can basically learn to code by making music. So you can program all these different tracks, and so it supports live coding. So this study here, we implemented a chat and also a shareable script, so that you could join with different live coders and edit the same code in this script. And so we use, as you can see, FirePad and FireChat for this. And so this video is about 3 coders, live coders, that are speaking in here, and they are the 3 located in 3 different rooms and cities. And we analyzed this experience using autoethnography, and so reflecting back how we experience the live coding together. This is another example, moving to asynchronous remote, and you will see it in a minute, and on wearables. So this project was done at Queen Mary University of London, and it involved three main teams: the e-textiles team with Sophie Scaff and Becky Stewart, and then the Internet of Musical Things with Luca Turquet and Mathieu Bartet, and the Audio Commons team with Ariane Stolfi, Mathieu Bartet, and myself representing the project. And basically here we were exploring the notion of having a hoodie with sensors attached to the hoodie that could modify by gestures sounds downloaded from the internet in essence. And we were using Bela for this so that it could be an embedded experience. So we can see the video here. And the way of evaluating this experience, we borrowed and adapted the method called technology probes, where you create workshops and create like this, showrooms, showcases. People can wear and explore the interface, and then, or in this case, the experience, and then provide feedback. So we adapted these methods. Okay, another example which is slightly different but still in this matrix is collocated synchronous. It's bringing the participation, and I can already show the video, but basically there's with web audio all these new possibilities of creating mobile applications and create music and then involve the audience for that. So together with Gerard Roma, we've just written this paper exploring this approach of performing audiences, and we just created 13 dimensions trying to understand the pieces that we've been creating in the past, but also in order to understand future pieces or create future pieces or evaluate them. And these dimensions include the interaction between or role between the performers and the audience performers, but also looks into the technology, the role of the technology, the role of the computer system, and so reflecting back on this period in a way, as you've seen, research methods, sometimes you need new research methods basically to understand new phenomena. And so this continuum here represents a way of exploring these new research methods depending of what you want to do research on. This is inspired, or this continuum comes from research together with Kerry Jewett and Sarah Price, where we were looking into commonalities and differences between research methods in social sciences and the digital arts when exploring the body, but that this continuum can also be applied to other domains where you need research methods. But basically, to give an example of it, we've seen that you can expand a research method just staying in the same context as we've seen with video analysis and musical tabletops, or you can resituate an existing method in a new context, as we've seen with the in the wild research, where it's still ethnography, but you're moving to the wild and you're exploring a new practice, as opposed to ethnography that would observe existing practices. Transferring an existing method to a new discipline is another approach, as we've seen with live coding and the autoethnography. We are just moving the ethnography to a new discipline, which is live coding and music making. Finally, generating new methods. Technology probes would be the perfect example, where you combine cultural probes approach together with workshops and showrooms and that kind of combination, where you're creating a new method. And yes, that's takeaway message of this phase is that basically for new phenomena you might need new research methods that do not exist. So to move on, HCI and SMC are two disciplines that are based on technology, and they move and change rapidly. And so we need to also adapt to these new changes. So this is Being Human, another roadmap that was published in 2008, looking forward about HCI and how all these socio-technical transformations would change the behaviors and the way of approaching new technologies, and also for us designers of these new experiences and ecosystems we need to be aware of and consider. And that ranges from ubiquitous computing and the interface that is everywhere, or this pervasive hyperconnectivity where you are connected all the time and invades both not the public sphere only, but also the private sphere, or artificial intelligence and how it is in a way being more present in all the disciplines. So how, and then the interaction with artificial intelligent agents, how to control them and not they controlling us. So this is a kind of discussions that we need to be aware. So the fourth wave HCI is a current discussion. First of all, whether there is a fourth wave in HCI, and secondly, how it looks like, what are the characteristics. And so in the discussions, which are open as I mentioned, it is mentioned that values need to be considered, ethics need to be considered, and so on. So here I would like to highlight three perspectives that I think are interesting to consider moving the field forward. One is sustainable interaction design, and the idea of bringing sustainability when we design and evaluate systems. So that means also considering the community, considering the long-term design of the artifacts we build. Feminist HCI also is an important aspect to consider, and that means feminism not only as an analytical tool, but also as part of this process of designing and evaluating experiences and ecosystems. It's a lens that we can use. Last but not least, decolonizing HCI. This connects very well with all this social justice and kind of when building tools, empowering those voices that maybe lacked the knowledge to build those tools, or lacked the kind of the platforms to build those tools, but basically reconsidering and reflecting about the tools we build and whether all the voices are represented. As a couple of examples of work that I've been involved lately that take this approach, one is this Wonomute network that I started when I was at NTNU and University of Oslo, where we created this edition of Wonomute seminar series and interviews, inviting great expert women in music technology. And so you can find the interviews and the seminars online. And so we created this space of discussion and community. The interviews were led by Carolina Jawad, who is a master's student at NTNU. She's now writing her thesis inspired by these topics, and I'm supervising this work. And so this is part of her kind of early findings. You can have a look at the publication of her master thesis, which will be this summer. But just to highlight, she conducted an online survey gathering more than 100 voices, asking about gender HCI and for audio and music hardware, in particular whether we perceive gender when interacting with music technology. And so, as you can see in this continuum that Carolina is working on, interestingly, you find in the spectrum all these different artifacts, but none belong to this or are perceived as female or female, predominantly female. That's an interesting finding. But yes, keep an eye on the research, and this actually, so this research was informed by all these interviews and this community that we created, and it will inform, hopefully, industry, academia in a next stage. Another project is this Milk Auto, a virtual agent for music information retrieval in live coding, which is a collaboration with Eclectic, Leicester Hackspace, Luiseg, Phonos, and MTI. And it's awarded with an EPSRC HDI Network Plus grant. Basically here we are exploring collaboration with a virtual agent, but also what would be then this nature of collaboration with this virtual agent, who controls who, all this will be explored, but also different levels of collaboration will be explored because it's built on top of a tool, an existing tool already, Milk, which is basically gathering sounds from free sound, and this connects to this notion of asynchronous remote collaboration with users who provided this big database. So, and then we will share the tools through workshops and concerts, so also keep an eye on it. I would like to conclude with a quote by Margaret Atwood, and also connecting with her fantastic keynote at CHI 2014. And this notion of science fiction informing technology and technology informing science fiction, and this mutual interaction, which I think speaks to how HCI and SMC inform each other. And so we are agents of change. We have the tools to do so, but we also have the responsibility to do so, and we can basically create a better future. And I think that's what I wanted to say. Now we can move from this asynchronous remote interaction to a synchronous remote interaction. So I'm happy to take any questions or comments. Thank you for listening.
Andrea, I have the same question. 1, 2, 3, 4. All right. Hello, everyone. I'm Haralampo Saitis, or Haris Saitis, from the Centre for Digital Music at Queen Mary University of London. I'm one of the scientific chairs for this year's virtual SMC. So good to see everyone, and thank you for participating. I see we have about 120 people watching right now. That's great. And as a reminder, during the live Q&A sessions, please poster your questions on the YouTube live chat, and I will try to summarize as I talk with Anna. And first of all, welcome Anna to SMC 2020, and thank you very much for this very inspiring keynote presentation. I will start, I guess, with a question which is similar to Andrea. So Andrea and I kind of had the same question immediately. So you just talked towards the end of your talk about gender perception, so gender encoding in music HCI. Could you elaborate a bit on the perceived gender-based cues?
Yes, sure. So hi, welcome. Well, thank you. So basically, well, this, as I said, is work from Carolina Zawad, and so I will talk on her behalf. Maybe she's in the chat and might would like to add a comment. But gender perception in music HCI, or is seeing whether these artifacts, and in this case audio hardware, which is what Carolina is bringing as a new object to observe, is whether we perceive them with a certain gender, and that means, so do we perceive it as neutral object, or does it is it perceived as male oriented object or female oriented object? And so the main cues you were asking, one is shape, whether rounded shapes or squared shapes that can maybe incline the user to see it in one way or in another, but also color. And yeah, Carolina was mentioning that white colors tend to be more seen as more neutral or more female objects rather than perhaps black colors. But yeah, this would be the kind of cues. Also, the wording might also influence the wording that includes the naming or the naming of the artifact of the product, but also maybe how you sell that product. So it's quite a complex world, and that's what Carolina is exploring at the moment. Maybe she's there. And Carolina, do you want to add anything? No.
Great. Thank you very much for this, and it's very interesting, actually, this kind of connection with shapes and gender. So another question I would like to ask is about, in the earlier part of your talk, your work on collaborative art, collaborative interaction. Have you thought about or even done work on applying this for, let's say, collaboration between someone with a sensory impairment, let's say a visual impaired person or a hearing impaired person, and somebody that is normally sighted or normally hearing? So a collaboration aimed to help the sensory impaired, and how collaborative art could work towards that direction.
Yeah, so that's I think so. Even though I have not worked myself with particular communities, during the research with Reactable, we were exploring this idea of the multimodality, or how to give information using different modes, not only the auditory mode, but also visual mode, and even the haptic mode, as a way of satisfying different ways of perceiving and understanding information. And it's, I mean, you can find research and collaboration with particular communities. But yes, it's a topic I'm interested in exploring more. But yeah, the abstract answer would be using different modalities seems to be a way of supporting different kind of ways of perceiving. But yes, thanks for the question.
Thank you for the answer. I'm trying to see if there are any more questions in on YouTube. I think a couple of attendees are asking if they can somehow access the bibliography of the talk, but I think people can go back and look. I mean, these videos will be streamed on demand, so people can go back and find out the information they need.
Yeah, well, I'm happy to share the. Yeah, I was thinking about that too. So it's I'm happy to share the reference list, either it can go together with the video and or also on my website. I can share the list, the bibliography list.
Okay, that's great. Yeah, I think people can contact you perhaps directly. Great. So I think I don't see any more questions. I don't know if my colleagues at SMC have some questions they would like to ask. Okay, it seems that there are no more questions, so maybe we can conclude here. This was really interesting, and I'm also personally interested in exploring cross-model associations that are very characteristic of auditory cognition, and this could be explored both in artistic but also in more, let's say, healthcare well-being scenarios. So yes, I think that's it. Thank you very much again.
Thank you, Charis. Thank you.
It was great having you, and thanks to our tech, Carlo, and to Andrea and Simone for this wonderful effort. And we will be continuing in a few minutes with the next session. Thanks, everybody. Bye-bye.
Thank you.
Hi, my name is Hans Lindetorp and I wish to present Web Audio XML for you today. We are proposing a new standard for structuring web audio. And the study is done by me and Kjetil Falkenberg. And we are from Royal College of Music in Stockholm and Royal Institute of Technology in Stockholm, Sweden. So, what is Web Audio XML? It is an XML language for structuring audio graphs. It lets you connect audio parameters in an audio application to external events and variables. It's built upon something called Web Audio API, which just 2 years ago became a web recommendation. And that is great because that means that Web Audio API is available on almost all devices with a web browser. That makes it possible to build audio applications that could be online and you can share it with just a link. And there are lots of projects running already, professional, pedagogical, and more like researcher applications. At the Royal College of Music, we have an education in music production. And those students are great. They love audio, they love music, they love technology. So they could potentially be great contributors of applications using Web Audio API, but they don't know how to program. So just to learn as much JavaScript that would be needed to be able to do something interesting, that would take a long time for them. But they know some HTML because we have like basic classes in web design connected to music. So that was why we came up with the idea to do something with XML, which is fairly similar to HTML. So that is Web Audio XML. And before we dive deeper into the technology, I want to show you 3 examples of what you can do with Web Audio XML. And the first example is a synthesizer. It's online, and it's actually running right now online from CodePen, a CodePen project. So you can see to the left here the graphical interface, and to the right the XML code. And I am playing the synth from my external MIDI keyboard, so it's using Web MIDI API as well. So it works like that, and it works like expected. You have the attack, sustain, decay, and release. And we can change, this is an FM synth, so we have a modulator and a carrier oscillator, and we can change the pitch of the modulator, which changes the sound quite dramatically. Okay, so that was playing on the synth. This is how the synth is built using Web Audio XML. So you can see 2 chains here. One for the modulator, which is outputted to the carrier down here. And both oscillators are controlled. The gain of the oscillators are controlled with an envelope as well. And those values, attack, decay, sustain, release, are connected via the follow attribute to the graphical interface. So that's how it's working. Next example, that is a very simple game, but it gives you an idea of how you can use Web Audio XML to do game audio. So we have a spaceship and an enemy. As you can hear, the sound changes depending on how close I get to the enemy. We have sound effects as well. Oops. And the higher the score gets, the more music I get. And this application was built like this. So we have the music up here, 2 loops running through a gain node controlled by the score, and a bytecode filter set to low pass, also controlled with the score, mapping the value of the score to frequency values for the filter. We have the spaceship with the bandpass filter and the Q value that will follow the distance to the character from the enemy. And then we have a whole bunch of sound effects as well. So that's how that's built. The last example is very new. We just got it. It's one of the student projects. It's done for smartphones. So it's kind of a game. You're supposed to press this button. And hearing the sound. And then you're expected to imitate the sound. Well, maybe not exactly. So, but as you could see, the sound changes on the x-axis and the y-axis. So it's the formants that are changing. And this is how it's built. So we got the oscillator running through 2 bytecode filters, and the Q value and the frequency values are following and the relative X value and the relative Y value and mapped to sensible values. So, what does Web Audio XML offer? Well, it offers a hierarchical structure that gives a picture of the audio graph when you code it. It's a relatively easy entry into audio development for beginners, and it also offers rapid prototyping. And it helps creators to focus more on the artistic ambitions and visions rather than all the technical aspects and issues that you might get stuck in. What is done so far? Well, we've set up a GitHub page with open source code and documentation so people can learn, dive into it, and maybe contribute as well. We have a CodePen collection with lots of laboratory examples where, for example, students can go there and try out the examples and learn by changing the code themselves. We also set up a YouTube playlist with tutorials to make it easy to get started. How did we do this process? So it started off with years of experience with student projects using Web Audio API at the Royal College of Music. And that brought us, as I told you, to the point where we thought we should try something else, and we tried the XML approach. And we built a prototype and evaluated it with a group of sound and music computing experts in Stockholm. And the feedback we got from that session took us to the beta phase that was evaluated with professional composers and music producers at the Royal College of Music. And the feedback we got from that session took us to version 1.0 that was released and tested during the spring with more than 25 student projects. And we just got the results back, so that's great. And what did we learn? Well, the feedback we got both from students and experts was that this technology is great for learning. It's great for prototyping and for sharing ideas and productions, small productions. And also good for collaboration when you could use, for example, CodePen to write code together. But they also expressed some needs and wishes. For example, professional debugging and testing tools to be able to use the technology more smoothly. And they also asked for modular structure with the files, with shareable components that could be put in repositories and shared with the community. So that's actually built into the current version of Web Audio XML. We also got a request for a JavaScript API. So when you build a structure with XML, you might actually want to go further and to do exactly what you want with that parameter in the graph. So they asked for a JavaScript API to do that specific task with the audio parameters. So what is next? Well, we are currently doing a follow-up study on those student projects to see what they did, to see what they learned, and so that will be exciting. And we're planning to present it in December this year at the Web Audio Conference, where we also want to discuss the potential for a future standard like Web Audio XML. It would also be great to open up the technology for JavaScript plugins like web audio modules and web audio plugins, maybe even WebPG. So that would be really great. And with those words, I want to say thank you very much for listening, and please visit the GitHub page, and don't hesitate to contact us if you want to collaborate or if you have further questions. So thank you very much.
Okay, we are ready to start now. Thank you for taking the time out of your busy schedule. I'm Shinkato, the student of the University of Tokyo. Today, I'm talking about Web 360 Square, an interactive web application for viewing 3D audiovisual contents. This is today's outline. First, I will talk about the introduction, our research background, and then I will introduce 3 methods of 3D sound representation and 3 interactive 3D audiovisual services. Next, I will talk about my study, Web 360 Square, and summary of questionnaire responses, and finally talk about future work. Okay, let's start. In recent years, the use of video streaming services has expanded rapidly. According to the 2018 Global Internet Phenomena Report released by Sandvine, video streaming accounts for about 58% of all downstream internet traffic. With the continuing adoption of VR services, 360-degree video streaming has also attracted. YouTube, Facebook, and Netflix offer support for 360-degree video and 3D sound. Those video streaming services have applications for web browsers in addition to dedicated applications. The web is an environment that anyone can easily use, and now supports the playing of 360-degree video and 3D sound, for example 3JS, A-Frame, or Web Audio API. But there are a few web applications that can play 3D content interactively. In our study, we designed and implemented a web application called Web 360 Square, which plays 360-degree video and object-based 3D sounds. Various methods exist for representing 3D sound. MPEG 3D audio, which is a 3D audio standard, supports 3 methods: channel-based, object-based, and higher order ambisonics HOA-based audio. First, channel-based audio is known as traditional 2.0 channel stereo sound, and there are 5.1 channel surround sound or immersive sound with additional channels. It provides optimal sound performance for a predetermined number of speakers and speaker layout. However, it lacks flexibility and interactivity. Object-based audio uses sound objects which have spatial coordinates, and it renders optimal 3D sound for speakers in real time using those coordinates. In addition, each sound object is managed independently, so object-based can use flexible and interactively. Higher order ambisonics, HOA-based audio records a spherical sound scene spread around one point. The spherical sound scene can be easily rotated in synchronization with the listener's head rotation. HOA is also flexible for speaker layouts, but HOA doesn't have clear spatial information, so it's difficult to access each sound object in the sound field. I will introduce 3 interactive 3D audiovisual services. Inside Music is an experimental website published in 2017 by Google Creative Lab and Song Exploder that uses JavaScript frameworks of WebVR and Web Audio. You can enjoy 3D sound with object-based audio in a virtual space on the web. It is not necessary to install a dedicated application. Only a web browser is needed. In Inside Music, only object-based sounds, not 360-degree videos, are mapped in a virtual space. In our previous research, we designed and implemented STM360 Square and Vibration, which are interactive 3D audiovisual services for tablet devices or VR head-mounted displays. Both systems were developed using the Unity platform, not web. Here talk about Web 360 Square. We designed and implemented the interactive web application for 3D audiovisual. In the table, we summarize a comparison between the related systems and Web 360 Square. The most important point is the environment is the web. Then the comparison target is Inside Music, but as discussed earlier, Inside Music doesn't use 360-degree videos. Our Web 360 Square is published on GitHub pages. The URL is on the slide. This system is built with A-Frame and WebOD API. Let's give you a short demonstration. When you move the tablet device, the view angle is changed by a gyro sensor. Tapping the front cyan sphere toggles play and pause. You can turn each sound on and off by tapping these audio visualizers. When you turn to the right, you'll hear the sound from the left. If you wear a headphone, it's especially easy to hear. Another content is a concert. This figure shows the overview of system design. The processes in A-Frame are mainly to project 360-degree video on a virtual space and to map audio visualizer onto it. A-Frame also changes the viewing angle. Web Audio API renders 3D sounds in real time and gets frequency data of each sound source. The left figure shows the system implementation. This dashed border field represents the A-Frame process, and this field represents the Web Audio API. The middle field here is for connecting the two fields. The right figure describes the process of an audio visualization. Frequency data is obtained by the Web Audio API on each tick, the order of 60 to 120 times per second. We extract the upper and lower limits of the frequency in which a valid value has appeared at least once, and define this band as the valid frequency band. Then the valid frequency band is divided into 32 groups. The average value is calculated within each group. The audio visualizer has 32 needles that have one-to-one random correspondence to the 32 valid frequency groups. We conducted a subjective evaluation of the Web 360 Square through a questionnaire survey that was carried out at the Interrupt Tokyo 2019 between June 12 and June 14. We prepared 2 sets of iPad tablets and headphones and accessed Web 360 Square on Safari browser. The subjects were 93 visitors to Interrupt Tokyo. First, we provided an overview of the application and explained how to use it. We then let the visitors freely play with the application and evaluate it. After the experience, the visitors completed their questionnaires and we acquired the evaluation data. The questionnaire contained 6 questions as shown on the slide. It was evaluated using the 7-point Likert scale, ranging from 1 to 7. 1 is very poor, 4 is fair, and 7 is excellent. This figure shows the result. The middle of the response of 4 is aligned with the origin of the horizontal axis, while responses of 5, 6, and 7, indicating good evaluations, are arranged in the right direction, while responses of 3, 2, and 1, indicating poor evaluations, are arranged in the left direction. As you can see, it is highly rated overall. However, there were not a few poor evaluations for question 3. Question 3 inquired about the 3D effect of the synthesized sound. We believe that this was caused in part by the ambiguity of question 3. It is thought that multiple elements, including direction, depth, and spatial realism, form the 3D effect of sound. It was difficult to the subject to clearly understand which element the question was referring to, and we didn't know which element the subjects were referring to. Therefore, we will more carefully verify the precision of our questions in future surveys. In the future, we will promote integration with STM ontology. What is STM ontology? STM ontology can describe the multimedia recording metadata in a layered structure. The metadata is, for example, the location information, the orientation of the musical instruments, the venue information, the recording process, and so on. We will promote integration and fetch the metadata used in Web 360 Square from STM ontology. And we also improve and add features and fix bugs on Web 360 Square. In addition, we would like to carry out the network performance evaluation. This is all for my presentation. Thanks for listening.
Hello all, I am Federico Simonetta, and together with Federico Vanzini and Stavros Talampiras from the University of Milan, the Music Informatics Laboratory, we have written this paper about an automatic framework for compiling multimodal datasets with audio and scores. The main motivations are explainable with 3 keywords. The first one is multimodality. So the idea that we can exploit multimodal data, so different kind of data such as video, music recording, lyrics, images, and so on, for common MIR tasks. We think that the web already allows end user to exploit multimodal approaches, but the problem is that we need data sets to train and to develop multimodal computational techniques. A second motivation is to improve the reproducibility of the research. Reproducibility is one of the main concerns of contemporary scientific research, and in music information retrieval it usually occurs due to differences occurring in various implementations. For instance, different data formats used in music or different parameters used to load data. The third keyword is generalization. Generalization has gained attention due to the rise of machine learning. The thing is that we need to increase the number of well-annotated datasets for training effective models. Many of the MIR methods are trained on datasets, very little datasets, and they have a low ability to generalize when tested on different datasets. The design principle that moved our effort are 6. The first one is generalization. In this case, we mean the ability of including different datasets which are distributed with various formats. So we want a framework that is able to provide multiple datasets, even if they are distributed with different formats. Then we want modularity. So we want to be able to use datasets in different contexts. For instance, we want to reuse existing utilities to include additional datasets, or we want to use only some part of the datasets, not all of them, and just some annotations. And then we want that the framework is extensible. So the end user should be able to convert from existing formats to take advantage of the API that the framework provides. And we want that new datasets can be added without having to edit sources of the framework. Then we want that the end user is able to do set operations over all the datasets provided by the framework. For instance, one of the major trends in music performance analysis is analyzing piano music. This is because we have these claviers or similar piano, which allows us to record very precise MIDI recordings. But there are also other instruments other than piano, and a recent trend is to focus on other instruments. But we have few data, and the annotation of this data is very time expensive. So one thing that can help is to merge different datasets and take all music pieces using violins, for instance, or using flutes from different datasets. There is another point about copyrights, because we want that all datasets provided by the framework are downloadable from their official sources, so that we don't have problems with copyrights. And then we want that the framework is audio to score oriented. Of course, this is just for now. This is our major concern, because the framework is poured in an audio score research. So we augmented all the data available to increase the alignment data usable in our research. This is a picture which shows the overall infrastructure. As you see, the API is the main object from the end user perspective, and the API contains references to the official files, JSON files, but it can also contain references to custom files. In particular, there are two kinds of files. There is datasets.json, which contains the reference to a dataset directory. This is the official one. This is the custom one. We can use different datasets.json, for instance. And then there are the definition files. So maestro.json, backend.json, smd.json, and so on, which contains references to the single files inside the dataset directory. Everything is relative, and everything is very modular and can be distributed on different hard drive. A dataset definitions, so these other custom definition and Maestro, Backend, and SMD. A dataset definition is essentially a JSON file which contains generic description of a dataset. These are some example of fields contained in a dataset definition. For instance, we have the ensemble. Can be true or false if the dataset contains ensemble music pieces or not. Instruments, the list of instruments used, the recording format, the installation command needed to download the dataset, the ground truth type contained in the datasets, and the list of songs with other attributes. And once a dataset has been described with a dataset definition, which must be done by hand, we can use the dataset definition out of the box with our API and together with other dataset definitions or the official dataset definition. So everything is very modular. The annotation files can be stored anywhere else, and there are three different levels to describe the ground truth. So each dataset contains a list of ground truth, and the ground truth contains all these parameters, so precise alignment, broad alignment, and so on. Each one of these is a ground truth type, and each one of these is associated with a values, which can be 0, 1, or 2. 0 means not available for a dataset, and 1 means that it's available and has been manually notated, and 2 means that it's available and it's created by some state-of-art method. As I said before, we augmented all the data with alignment. We have only few datasets which contain both music score and aligned data. So we analyzed these few datasets and computed the histogram of the mean deviations of the notes and the histogram of the standard deviations of the notes. Actually, the mean is computed per piece, while the standard deviations is computed per notes. So this is slightly different. We end with 4 different histograms, 2 for the onsets and 2 for the offsets. And so we have onset mean, offset STD, and onset STD. And note that these onset and offset actually are onset deviations and offset deviations from the aligned data. Then when we have a non-aligned piece, for instance a piece recorded by a disc clavier, we take an onset deviation mean from the histogram of the mean and for the whole piece, and an onset deviation STD for each note, and we add it to the onset mean and get an inferred onset deviation. This happens the same for the offset. Okay, this is just a simple way to reproduce a distribution of the deviations, but there are actually no effective method as of now to infer the music score from a music performance MIDI. And so for now we are still relying on this simple method. By the way, we empirically checked that the alignment methods, the alignment state-of-art alignment algorithms work almost the same on music scores and on inferred misaligned notes. The API are written in Python, so they basically are written in C. They allow to load different definitions other than the official ones. They allow to filter the dataset based on attributes, to retrieve data with different kind, like piano roll or the note matrix, like the MATLAB toolbox or the MATLAB MIDI toolbox or raw data. They allow to parallelize the computation over all the songs, and it's completely compatible with PyTorch. Now let me show you a couple of use cases. The first one is when the user wants to use our framework to convert an existing dataset. In that case, he just has to describe how to convert from the input file format to the output to our annotation type. For now, he still has to do this command, the copy prototype GT. It will be not needed in future when we'll completely move to a object-oriented approach. But for now, this method is still needed, this command. And afterwards, it just open the file, in this case a CSV files, and fill the dictionary. This prototype GT is basically a dictionary, an empty dictionary with the correct fields. And the magic happens here in this convert, which allows the framework to apply this function over all the files. In this case, we show a couple of methods. For instance, here we instantiate a dataset class. We filter it according to the specification. In this case, we take all music pieces with piano, which are not ensembled, so solo piano, written by Mozart, and which contain a precise alignment annotation. We can get the raw data, we can get the mixed track, the ground truth path, we can get the piano roll. In this case, is the piano roll with timings referred to the non-aligned data, so to the inferred data. And here we show that we can just define a function which works on a given data set and on a given index on the data set, and we can process a song inside this function and then apply this function in parallel to a whole data set. In this case, the data set is filtered by violin. The third use case is when a user wants to use PyTorch. In this case, he just has to write his dataset class as would do in PyTorch, but he just has to inherit from dataset. In this way, he can filter the dataset, and in the getItem method, for instance, we can get the score or get the piano roll and convert it to tensor and send it to the GPU and so on, and we can iterate over this my dataset object to have all the magic of PyTorch, which is able to load data using the CPU while the GPU is working on other data and so on. This is our short to-do. We can, of course, improve the conversion procedure, as I said before. As suggested by reviewers, we can study the user experience. We can add, for instance, the estimation of the download time needed for each dataset, and this can be useful, for instance, if in a music computing class one wants to let the students try to test some experiment on a little dataset. We can add new annotation types. We can leave the user the ability to distribute only some of the annotations. Of course, we are open to any contribute, any perspective, any advice. There's also another project written in Python about datasets for music information retrieval, but this project in particular is about multimodal. So if you are interested in music information processing with multimodal approach, just have a look at the paper, let me know, and I'm sure that you have something with which you can contribute to this framework. You can just install the framework using pip. This will install the Python code, but then we need to load and install the datasets with this command. And here are the links for the docs and the source code. Thank you for your attention.
Hi, my name is Laura Bishop, and I'm a postdoc at RITMO at the University of Oslo. My research looks primarily at social interaction and coordination in music ensembles, and a large part of this involves studying musicians' body motion when they are performing together. In this presentation, I will be talking about a comparison that we made between two infrared motion capture systems during a recording session with a string quartet. There are different types of motion capture technology that are regularly used to capture human motion. These range from video, where you can apply different computer vision and pixel differencing techniques, to inertial sensors, which sit on the moving body and typically track some combination of orientation and acceleration, to optical motion capture, which uses triangulation to track the position of certain markers in 3D space. This is the type of motion capture that we're talking about. Our comparison was between two passive tracking systems, which use infrared to track the position of reflective markers through space. Some previous studies have been done to compare mocap systems in terms of noise level or drift. Our experiment here looked at tracking reliability, including noise level and drift, for both stationary and moving markers. At our center, we apply motion tracking to a variety of different scenarios. Some involve capturing fairly large-scale motion, like musicians' bowing gestures. Others involve capturing quite fine-grained motion, like pianists' finger movements. There are also some studies that have looked at motion during standstill. We know that different types of motion provide different challenges to mocap systems. For example, with standstill, your data can be easily degraded with high noise levels. And for situations with higher amounts of motion, in particular with faster velocity, so you have to ensure that your tracking system can sample the motion data at a high enough frequency so that it doesn't lose track of the marker as it's moving through space. So we compared a high-end mocap system with a mid-range mocap system, and it's important to note that the high-end system that we used was about 10 years older than the mid-range system at the time of these recordings late last year. To tell you a bit about the framework of these recordings, we basically had the opportunity to do a recording session with the string quartet from a music academy nearby us. This session had two aims. First, we were making an empirical test of some hypotheses relating to inter-musician communication. And two, we were testing equipment in preparation for a later study. We ended up with successful recordings of the session from both mocap systems, which allowed us to make the analyses that I will present in a moment. So we made a total of 7 recordings. The musicians were seated in the center of the capture space, and they made multiple performances of one particular piece, plus some additional performances of other material. For most of the performances, they were configured as you see in the picture here, which is the normal configuration for a string quartet. But for some of the performances, they were configured differently, for example, sitting back to back. The musicians wore 6 body markers each on the head, back, and 2 on each arm, plus 4 markers that were attached to eye tracking glasses that they were wearing. And these comprise our moving markers. We also had 4 markers attached to each of the music stands, and these comprise our stationary markers. So here at the right, you see some examples of trajectories of stationary markers. The position values here are given in terms of the marker's distance from its starting position. This is done so that we can see the position values for the two systems together on the same axes. You'll notice that there is a small degree of noise in all of the signals, and there are also some what we could call instantaneous spikes. For example, in the top plot for the mid-range system in blue, there are a couple of these spikes. And then in the second plot, the middle plot, for the high-end system in red, there's a small jump that takes place around 35 seconds, where the position of the marker changes very, very slightly and continues in the new location for a period of time and then goes back to its original location. So we observed some different types of noise here. At left, I've listed the variables that we looked at for stationary markers, which I will explain in a moment. For moving markers then, at right here you see a few example trajectories of some of the cellists' markers. These are also represented in terms of their distance from their starting positions. As you can see, the trajectories recorded by the two systems are almost but not quite identical. And in particular, if you compare the first plot on the top to the second one, you can see that some of the markers recorded with higher degree of similarity between the two systems than others. For moving markers, we looked primarily at the magnitude of error or difference between the systems as a function of quantity of motion. So we looked at the noise level in stationary markers by measuring quantity of motion measured in millimeters per second. You can see our results in the plot to the right. We actually found higher quantity of motion, so higher noise, in the high-end system than in the mid-range system. And this was the case for all of the 7 recordings that we made. You'll also notice that quantity of motion generally increased across recordings 1 through 7 for both systems, which suggests that precision decreased over the course of the several hours that this experiment was running. We also looked at the spatial range that was captured by the two systems. This is measured in terms of the difference between the maximum and minimum position values. You can see the results here in the plots. Again, for all of the 7 recordings, we found that the high-end system had a larger spatial range than the mid-range system. So this again indicates a different form of noise level. Finally, for stationary markers, we looked at spikes. In the plot at the bottom, you can again see some examples of spikes in the signal. We looked at how often spikes came up, and we found that there was a consistently higher rate of spikes in the mid-range system than in the high-end system. So this was the case for 6 out of the 7 recordings that we did. For moving markers, we tested the hypothesis that the error between the systems, the magnitude of the error between the systems, would increase as quantity of motion also increased. And as you can see from the graph at the right, we did find, in fact, a pretty strong correlation between quantity of motion and between system error magnitudes. You can also see this in terms of the average between system error that we got for markers that sat at different locations. For example, for back markers, the back didn't move all that much and the error is quite small, but for the glasses, which moved quite a bit more, the error was bigger. For moving markers, we also made an analysis of the magnitude of errors for each of the x, y, and z dimensions. We found that the smallest errors occurred in the y direction, which was the vertical direction in this experiment. And it's interesting to note that quantity of motion was also lower in the y direction than in either of the x or z directions. So this may have played a role. So to conclude, I just want to summarize our results in terms of how they might be informative to people who are designing mocap experiments. First of all, we found that the older high-end system recorded with higher noise than the newer mid-range system. This is the case both for quantity of motion and for spatial range. So even though high-end systems like Qualisys can be preferred for some of their features like higher frame rates, better labeling algorithms, more affordable systems do give very high quality data at this point. We also made the important observation that between system errors increased with increasing quantity of motion. And this should be noted in studies where large amounts of motion are expected and probably accounted for with smoothing. And this should also in particular be noted in studies where precision is important. For instance, if you're looking at fine-grained motion like rapid finger movements. We did not find substantial drift within recordings, but we did find that recordings became less precise over the several hours that we were running this experiment, which shows how important it is to recalibrate if you're going to have a very long recording session. And I also want to note that we observed poor tracking in markers that were located near the edge of the calibrated space. This manifested in terms of high dropout as well as very high noise levels. We actually excluded these markers from our analysis because they were quite clear outliers. So this shows how important it is to make sure that your markers are centered well within the space that has been calibrated. Finally, I just want to thank our collaborators at Ritmo and of course the musicians who participated in this experiment, and thank you for your attention.
All right, so thanks for these great presentations and projects. This is the Q&A, and so the idea here will be to gather questions from the audience, from the chat, and maybe we can do a round of one question for each, and then ask more questions in terms of group questions. So we will start by sequential order, and we have a question from Andrea, actually, that goes to Hans. And the question is, do you think that your XML format can have a more general usage for encoding audio process and HCI interaction? For example, not limited to your specific application?
Yeah, that's a very interesting question, because we started off with this as being something for the web, using Web Audio API, but we had some discussions when we realized that this is actually kind of opening up for language to describe the connection between an interaction and an audio configuration. So yes, I think there is a great potential actually for like working on a language for describing those general things.
Great, thank you. And we move to Shin. So Shin, you mentioned in the paper, you mentioned that the current version, so it's built upon a previous version that was on Unity. So I was wondering, what are the advantages of using the web platform, and what do you miss from the Unity environment?
Yes, web. Sorry. Web environment is very easy. So Unity is needed a dedicated application, but web application is needed only web browser. So it is merit of our systems.
Thank you.
Thank you.
Yeah, and yeah, we just moved to Federico. So Federico, in your paper, you mentioned that you're planning to study the user experience of the framework. So can you outline what do you envision how this evaluation can look like?
Well, probably what we are doing is to let's try the framework, which is written in Python. It's targeted to developers, so probably we will ask to some research scientists to use the framework and to download it, install and test it, and we will just ask what they think and what could be the improvements with a very easy open questions and open answers. Not a real very precise plan for now, but we are open to any kind of suggestion.
Okay, thank you. And we move to Laura. So I just wonder how similar and different would be the results if you analyzed a different musical activity. And you mentioned the standstill. So I guess the extreme case would be a standstill. I'm not sure whether that would infer much, but yeah, how different would the results be?
I don't think the results would necessarily be that much different. The types of movement that we captured here were head movement and arm movement, which captures a pretty good range of what people tend to do. Perhaps if we were to compare something very fine-grained, like pianist hand movements, this would be perhaps interesting because it's quite a lot of movement, but it happens in a very small space. So this probably would be an interesting comparison to make. And in terms of the standstill, well, some of these analyses have been done previously in preparation for looking at markers that are standing very still. So some things that our colleagues are working on are trying to separate the noise out of movement that actually happens when people are standing still, and the markers are almost stationary but not quite.
Mm-hmm. Thank you, Laura. And so, well, looking at if there are any questions, feel free to post those in the chat. And if not, I have maybe like a group question for all of you, given that this is a session on hardware and software, and all of you in your papers discuss it about the standards in a way or in another, how to have a dialogue with standards and also make a sustainable progress of the code. So any thoughts for your respective projects on what are your plans in terms of making the code, or I mean, making the code according to certain standards, and if there are not standards, what would be your contributions? What are your thoughts?
Well, there are a number of standards for music representation in various formats, and we at LIM in particular in Milan, we develop a standard for multimodal representations, which actually is under reviewing in this moment. It's called the IEEE 1599. So that can probably be a suggestion, but well, it's based on XML, and maybe of course some revisions are needed. And also there are other standards for music representations in various formats, like the AMI or the Music NX that is developed by the W3C committee. And so it's a topic of research in trend right now, and probably the SMC community can give its help in developing new formats.
Yeah, I'm looking forward to see if we can do something with Web Audio API, XML, and then connect it to platforms like PD or other standards that we're using in this community. That I think every attempt to do something standardized and to meet with different technologies will open up endlessly of creative ideas and projects. That's very exciting, I think.
I guess for me, there's in the world of motion capture, there's a number of different systems that are quite standard across and quite commonly used across different institutes. So checking the reliability of each of these against each other, and noting, of course, as we saw in our study, that these results change quite quickly as the systems get slightly older. This would probably be valuable, and also to check this against different types of motion capture that can be used in different situations. So versus just what you can take from a video camera in a more ecological situation would be useful.
Shin, would you like add anything on Web 360?
Yes. So, sorry.
Well, you talk about this consortium, for example, in your paper, the Software-Defined Media Consortium. So what is the role when deciding?
Our systems, and in our systems, there are many bugs, and now so we have to approve and add features and fix bugs on our systems in the future.
Okay, thank you. And so let's check again if there are any questions in the chat. And okay, there is one question. I think I'm not accustomed by Rares A. I am not accustomed to Web Audio API, but what would the authors of the paper consider to be the biggest limitation of their proposed standard is in terms of sound synthesis capability?
So I guess that question is for me. Well, what we present is not, just so we understand each other, it's not the technology that makes the sound at all. It's just a way of describing how that web audio should be configured in an application. And there is a lot of discussion going on if like web audio API is a useful tool, what you can do with it, if the performance is good enough, all sorts of questions. There has been a huge step forward with a node called Audio Worklet, and using that node you can build kind of like whatever you want to do. And I think that's the way WebPD is implemented into web pages, for example. Then performance-wise, I would guess it's still problems related to using a web browser to do fancy audio stuff. But I'm just very I just think it's so interesting with the web technology, even if the performance is struggling a little bit at the moment. It's so interesting to see where we're going in the future, and I just think it will be a very important platform. And our attempt to specify that using XML is just like a first attempt, like a first sentence in the question. So let's have a dialogue about what we need to express and what we need to sort of define when we build things like this.
I also had a question for you, Hans, about why did you choose XML and not JSON? That's kind of explained in the paper, but lightly. So I just wonder, can you?
That's a very pragmatic decision. So I found that my students generally understand HTML quite well. And as soon as we get into, brackets, dots, curly brackets and stuff, they just get disorientated and they miss a little sign and it's just very corrupt. So they found it somehow easier to do it with XML. So that's the only reason. I know there are definitely downsides using XML as well. It gets quite big in terms of code and stuff. But the response from the students was very good. They see and understand what they're trying to do. So that was very positive feedback. And we are right now working on a follow-up study on 25 projects using it. So it's exciting to see.
Perfect. And so, yeah, Rares, thanks for the answer, by the way. Are there any other questions from the community, SMC? It's now your opportunity to ask questions. Yes, well, the chat is a little bit quiet, but then just to ask you all if you have anything else that you would like to add or complement from your presentations. No? Well, so then we can perhaps conclude this panel. I really, thank you for your nice presentations and contributions.
Thank you. Thank you very much.
Thank you so much. And yes, and just, please, there are applauses we can hear, so please keep, the next session of the SMC, which are the posters. Thank you.
Strings is an audiovisual installation in which we wanted to connect the idea behind the string theory in physics and the actual vibration of the strings. We have a subwoofer which is connected to a screw, which then activates the string, and then the sound actually travels all the way to the resonant box, and it is being then collected by 3 types of different microphones.
In my art practice, I'm trying to deconstruct certain ideas that normally we take for granted. In this example, we are analyzing what music really is, how sound is constructed, and what kind of connection it has with physics in a broader sense.
In this work, we present preliminary results of a project in which we investigate the possible soundscapes of the future. The starting point is a project by documentary director Eric Gandini, in which he investigates, among other things, how our working life and society will be in a future dominated by artificial intelligence and robotic automation. In this context, we asked, what will be the soundscape of the future? As a first step in our investigation, we organized a design fiction workshop at the Interactive Sonification Workshop 2019 at KTH in Stockholm. The results from the workshop are presented in the poster and in the related paper. Thank you for watching. We wish you a good vision of the poster and we look forward to an interesting discussion with you.
My name is Emma Frid and I'm going to present the work Haptic Music, exploring whole body vibrations and tactile sound from multisensory music installation. And this is a work that I did together with Hans Lindetorp. Sound Forest is an ongoing project between KTH Royal Institute of Technology, KMH Royal College of Music, and the Swedish Museum of Performing Arts. Sound Forest is a multisensory music installation that presents whole body vibrations through platforms in the floor. Within this project, we held a workshop focusing on perception of whole body vibrations with 5 composers. We asked the composers to stand on haptic platforms, and then they were asked to describe the haptic sensations that they could perceive. After that, we asked the composers to produce 5 multisensory music compositions for the Sound Forest installation. Our findings suggested that awareness of haptic music could be improved through training. We also found that there was a wide range of haptic experiences described for the same haptic stimulus. And this highlights the need for large-scale studies on whole body vibrations, especially in the context of music and music installations.
This poster introduces a tool to program the ESP32 microcontroller with a Faust programming language for real-time audio signal processing applications. Faust is a domain-specific language targeting high-performance audio signal processing applications. Faust can already be used to program other types of microcontrollers in embedded platforms such as the Raspberry Pi, the Bella, the Tinsy, the Elk, or the Owl, but here we demonstrate how such tasks can be achieved on the ESP32. The ESP32 is a series of low-cost, low-power embedded systems with integrated Wi-Fi, Bluetooth, and microcontroller distributed by Espressif Systems. Various ESP32-based boards target real-time audio applications such as the Liligo TTGO T-Audio or the Lyra T. These boards provide an extended external RAM module, which is important to have when running DSP algorithms with a large memory footprint. Faust programs can be turned into ready-to-use C++ objects for the ESP32 just by running a single command line or by using the export function of the Faust Web IDE. Generated objects take care of setting up the audio driver as well as carrying out real-time audio DSP in the background. MIDI and polyphony support can easily be added as well. For more information, please refer to the poster or to the corresponding paper in the proceedings.
This publication concerns an interactive audiovisual art installation based on a simple algorithm on the Sailor Automaton Rule 110. Actually, the installation is composed by a series of snapshots of the evolution of this algorithm, which are projected. We call those snapshots and those images as shadow paintings because they are projected on the wall or on canvases. The projectors, or the shadow boxes as we call them, were designed specifically for the installation and they offer a sculptural element. Actually, this paper discusses the process of creation of the work and the technical and the aesthetic considerations behind this project. The artistic language is minimalistic, and the aim actually is to express in a simple and a very elegant way the computational significance of this elementary cellular automaton. There is not much technological novelty in it, and the focus is more on the creation of a multi-sensory mediative microenvironment that celebrates the elegance of this algorithm, and it values a longer, slower, less dramatic and more sensual experience.
Hi, I'm Guilherme Yoshimura and just finished my master's degree at the University of São Paulo. This work is part of my thesis about classified speech disorders. In this work, we present a novel classifier that is based on the similarity profile built out DTW alignment MFCCgrams. We had the support of the School of Medicine that provide a database that contains 200 recordings of 2 Portuguese words widely used in SSD diagnosis. The first one is sapo, that means frog, and the second one is chave, that means key. The database was labeled as disturbed and normal by speech therapists, and 60% of the database were labeled as normal and 40% as disturbed. We compared the proposed method with 2 others SSD classifier, a classifier based on Earth mover distance, and another one that uses a relative DTW embedding known as MDTW. As a result, our method shows better F measure when applied in the word chave and a similar result in the word sapo.
Hello, I'm Nicolas Figueiredo, and I'm one of the authors of this article you see right now. And if you're interested in time-frequency representations or automatic music transcription or music information retrieval in general, this might be of interest to you. In this article, we propose 2 experiments that evaluate different features such as entropy, standard deviation of energy or amplitude, mean energy, and others, as estimators of musical information in the time-frequency plane. The idea is that with a good estimator, we can detect regions of a spectrogram, for example, that contain notes or harmonics or other musical elements. And on top of this, we propose an adaptive multi-resolution representation that would represent with higher detail these areas that contain relevant information for music transcription, and with less details the areas that do not. Of course, this is only the general idea of the article, and if you have any questions, please feel free to ask, and I'll be happy to answer them. Thank you.
Hello everyone, my name is Doabse Chowdhury from Karma, and I will be talking about embedding electronics and functional parts in the additive manufacturing process for digital musical instrument design. In this work, we introduce the musical implementations of embedded sensing by integrating sensors and passive components in the 3D printing process using fused deposition modeling technology. We test the proof of concept in 2 instrument prototypes, a variable interface to capture hand and finger gestures, and an augmented ultrafluid design. This method allowed us to design compact sensor modules, customizing interfaces, cleaner surface finish, and adhesive-free instrument augmentation. In this ongoing project, we describe the design methodology, implementation, and its possible applications for music. We further discuss its use cases, advantages and challenges, provide future directions for exploring applications of other electronics printing methods, and corresponding sensor designs. Thank you for listening. For more details, please see our paper. And if you have any questions, feel free to email me.
This poster looks at a recent kinetic sound installation called Menagerie that was presented at the Danish National Museum of Music in Copenhagen in November of 2019. Inspired by the collective behaviors associated with biological swarms, Menagerie is a kinetic sound sculpture that mechanically activates the deconstructed automatic rifle gun trigger as an autonomous sound object to evoke the repetitive nature of gun-related violence. Using statistics taken from the occurrence of firearm-related deaths from each U.S. state, 50 custom-fabricated gun triggers are subject to a variety of self-organizing and behavioral algorithms where they align, synchronize, and evolve, revealing the emergent polyrhythms inherent in American patterns of violence. More specifically, this installation uses a network of coupled oscillators to recreate the acoustic dynamics of swarms. The empty gesture of the unloaded cold clicking trigger is emblematic of the listlessness of political action and redress. In this piece, this sound is used as a medium through which the trigger swarm aggregates sonic mass to expose and sonify the timbral density of gun-related violence. This poster presents an overview of the compositional process involved in the design and fabrication of the automatic rifle triggers, the programming and sonification of the coupled oscillator network, and the aesthetic ramifications of composing for the trigger as a cultural object.
The objective here is to convey the richness of music through a visualization that should be accessible to non-music experts while being self-explanatory. So here is a prototype on Bach's The Art of Fugue. The visualization is performed real-time and will be presented in a concert next year by the Danish String Quartets. For that purpose, we needed to integrate a score following.
Hello everyone, my name is Georgios Fruitsos and I'm a PhD student at the Sonic Arts Research Centre in Queen's University, Belfast. This poster presentation is about the research I completed during my Masters. This paper talks about the combination of sonic arts and cultural storytelling regarding the peace walls in Northern Ireland. My main focus was on the peace wall between the Falls and Shankill Road in West Belfast, stretching over 2 kilometers in length and about 14 meters in height. These walls were placed during the Civil War, which began in 1969, referred as the Troubles. They were supposed to be a temporary measure. However, in 2020, these walls still remain, even though the conflict ended in 1998. The two artistic research projects conducted were to use audio to augment perspectives by forms of accessibility and engagement, as well to represent space and identity through sound. These were approached with a combination of socially engaged arts, urban arts, sonification, and the embodiment of sonic arts. The projects were created with the main concepts of spatial audio and sound walks. Project 1, Divided Spaces, is an ambisonics installation piece for an offsite experience, and Project 2, Peace Wall Belfast Sound Walks, is 6 mini compositions for an on-site experience. While both projects have different forms, they are connected by the dual purpose of the material gathered from the Peace Wall, creating new listening experiences to provide another sensory exploration through sound, and having art promote the discussion of conflict transformation and peace resolution in Northern Ireland.
Hello, my name is Marius Anoche, and I will be presenting the paper titled 3D ear shape as an estimator HRTF notch frequency. This was the outcome of a semester project I did at the Sound and Music Computing Master Program at Aalborg University in collaboration with fellow student Riccardo Micini and under the supervision of Stefania Serafin and Simone Espagnol, as well as Runar Untorsson from University of Iceland. So let's get into it. The broader field of research this paper is aimed for is spatial sound perception and rendering, of which one of the foundational blocks is the head-related transfer function. Head-related transfer functions are filters that describe the acoustic effect of the human head with respect to an external sound. They are formally defined as the ratio of sound pressures at the ear and in the free field as given in this equation. We can see that they are dependent on the frequency and direction of the incoming sound. Furthermore, it includes the effects of the human head, torso, and quite importantly, the pinna, which is the external part of the ear. All these are different from person to person, which makes the HRTFs highly individual. The aim of this project is to tackle this issue of individualization and work towards an accurate and handy procedure for predicting individual HRTFs from non-acoustic measurements. The focus throughout the project was on predicting the lowest frequency pinna notch, or N1, in the median plane. The reason why we focused on this is because N1 was found to be a critical cue for elevation perception, as well as the fact that there have been observed limited spectral changes compared to the median plane for azimuth variations up to 30 degrees. So moving plus minus 30 degrees from the median plane doesn't change much the progression of this first pinna notch. A lot of previous work has been based on the CheapPeak database, which is an extensive database of HRTF measurements for which 2D photos of the pinna were available. Based on this work, Raikar and others found good correlation between anthropometric measurements and the HRTF features. This in turn led to Spagnol and Avanzini, as well as Micini and Spagnol, to work on building some regression-based models aiming to predict the first notch frequencies of the HRTFs based on these 2D anthropometric parameters. For this current work, however, another dataset has been used, a rather new one, actually, one that hasn't yet been released, but one that is built on a dataset that has, in fact, already been released, called the Viking dataset. This unreleased version of the HRTF dataset had an extra focus on measurements in the median plane, as well as having been carried out in an anechoic chamber at the University of Iceland. As regarding setup, a standard Kemar mannequin was used, and a Genelec loudspeaker, which was fixed at a distance of 1 meter from the mannequin's head, with elevation being adjustable via an L-shaped rotating arm. Another key aspect of the dataset used in this project is the availability of interchangeable custom-made pinnae. Particularly, pinna molds have been created based on 20 human subjects of various shapes and sizes, which can be seen in this figure to the bottom left. Subjects have been named A to S, and in particular, also we have made a pinna mold of a standard Kemar pinna. An important thing to note is that we have available 3D scans of all these pinna models, which allows us to investigate certain HRTF features with respect to 3D properties of the ears. Moving on to the more technical part, the acoustical responses have been measured via the logarithmic sweep method. Particularly, an exponential sweep signal has been generated at the Genelec speaker, and which has been recorded at the entrance of the ear canal via a microphone. With this information, the head-related impulse responses could be computed via inverse filtering, essentially removing the sweep signal from the recorded measurements at the entrance of the ear canal. The frequency response of the HRIRs that were just extracted are in fact the HRTFs. When looking at them, however, we noticed quite a lot of reflections and shadowing, which we thought are due to the torso. Therefore, we carried out an HRTF measurement for a new subject, subject Z, where we had a flat pina basically. So we only had a microphone and no ear. The frequency response for this subject then isolated the effects of the torso and the head. Furthermore, we then derived a filter. We designed a filter to remove these effects. So we basically fitted this filter to the magnitude response of this subject, when applying this filter to subject Z, you can see the figure to the bottom left is a pretty flat response. This filter was then applied to all the other subjects as well. For the extraction of the notch frequencies at the various elevations, two methods were used. The first method was based on an algorithm proposed by Rijkaard and others, which involved a series of signal processing steps aiming to isolate these notches more clearly. These steps involved windowing the original signal, or taking the autocorrelation of this windowed signal and further windowing, eventually leading to a group delay function where the notches beneath a certain threshold could be extracted. The second method was a more straightforward method, where we extracted the notches beneath a certain threshold directly from a windowed HRTF spectrum, where this threshold was varied from subject to subject as the mean of the spectrum magnitude between 3 and 17 kilohertz. What we found was that the two methods generally aligned, and furthermore, we merged the two notch sets together. So if one method couldn't identify a notch, but the other did, we still eventually had that notch as identified. An example showing the extracted notches for subject A can be seen in the figures to the right, where the black crosses represent notch frequencies. They can be seen more clearly in the surface plot on the top. As mentioned previously, our focus was on the lowest notch frequency track, which typically starts between 4 and 7 kilohertz. What we did was that for each subject, we manually selected this track based on visual inspection. What we observed was that not all subjects show a clear N1 track, and in the cases where that happened, those subjects were disregarded. This left a total of 17 subjects. At the end, we were left with a total of 1,599 data points with which to play with. The figure to the bottom right shows the N1 track for all the subjects. Moving on to our analysis of the 3D pina molds and our desire to extract certain anthropometric features that could be correlated to the notch frequencies, we had the following approach. We went from the 3D scans to 2D depth maps, which are essentially pictures of the pina viewed from various angles in the median plane where the sound source may be coming from. This was done via a ray tracing procedure where we assumed that the sound is propagating via plane waves. What we did was basically send rays from the sound source towards a fixed grid of 100 times 100 points. This grid was chosen to be as the largest grid needed to project the largest pina at any elevation angle. Keeping this grid fixed allowed us basically to include the effects of the various sizes of the different pinae. Only intersection values above the microphone position were considered, and also shadowed positions were disregarded. That means that if we had multiple intersections from the same ray, only the intersection closest to the sound source would be considered. The figure to the top right shows an example of calculating such depth map at an elevation of minus 30 degrees for a subject, while the figure to the bottom right shows depth maps at multiple elevation angles. We now have all the ingredients to train a linear regression model, aiming to predict the first notch frequencies of the various subjects. What we can do is use the depth maps as predictor, but unfortunately the relation between the depth features and notch frequencies was revealed to be nonlinear when checking the assumptions for linear regression. Therefore, principal component analysis was applied to the data. Using the first 256 principal components, it captures approximately 98% of the total variance in the data and also satisfies the assumptions for linear regression. The training was carried out with a leave-one-out cross-validation on the subject level, meaning that when evaluating the regression for test subject A, the training is performed on the data from all the other 16 subjects, and so on when changing the subject. The main metric for evaluation was the mean absolute error. The reason why a linear regression model was chosen was in order to be able to compare our results with previous work. Particularly, Micini and Spagnol published a paper at last year's Sound and Music Computing Conference where they built a linear regression model based on 2D anthropometric data. They focused on an elevation interval between -45 and 45 degrees. This choice is evident when looking at our results as well, as very few subjects show notches above 45 degrees, and notch tracks for elevations below -50 degrees are quite flat. Therefore, we decided to train two models, one on the entire data set for elevations from -80 to 90 degrees, and one where we only used data from elevations in the -45 to 45 degree interval. The table to the right shows the results of the two models. The mean absolute error and the R-squared value of the fits are shown for each cross-validation case, as well as the mean and standard deviation of all cases. A weighted mean of all the cases is also introduced, where the mean absolute error of each subject is weighed with the number of predicted data points for that subject. This calculates the overall performance of the regression model by equally considering all individual data points, and is a more consistent metric. It's more consistent with the evaluation carried out by Micini and Spagnol. For our M1 model, we find a weighted mean of 532 Hz, which is a slight improvement to the 607 Hz found by Micini and Spagnol. Another metric for evaluation is to find the percentage of psychoacoustically valid predictions, which has been found in previous literature to correspond to differences of around 10% between frequency notches. This means that if two notches are within 10% of each other, they are perceived as the same notch. We find that out of all our predictions, 71.27% of them are psychoacoustically valid, while in previous work, 61.2% were found as psychoacoustically valid. In conclusion, a method for predicting the progression of the first notch frequency in the median plane of HRTFs with respect to elevation has been proposed. This method makes use of 3D anthropometric data, which is a somewhat novel approach compared to previous work, and it also shows a slight improvement compared to similar regression-based methods which used 2D features as predictors. The method could of course be validated and further improved by including additional data, as well as different machine learning techniques could be considered for the training part, perhaps something like random forest regression, which would not be constrained to the assumptions of linear regression models. Future work can also address higher frequency notches in order to eventually build a perceptually convincing individualized HRTF set. A list of references used in this presentation is shown here. Finally, I want to thank you for your attention and say that I am looking forward to try and answer some questions you may have regarding the project. Yes, take care.
In this talk, we will be discussing methods for performing with feedback in virtual acoustic environments. We will start with a few sound examples of artistic works that we have recently developed in this area. We will then move on to contextualizing our work, speaking a little about the history of feedback in experimental music performance traditions, and mentioning some of the techniques used for generating, controlling and suppressing feedback. We will then conclude this talk with a look at our novel methods for working with feedback in virtual acoustic environments. Throughout this presentation, please use headphones or good external speakers to hear the sound examples that we will play.
Is it still day? Day? If you like. There's no other word for it. Will it not soon be evening? Come on, Billy. Get up. You're beginning to incommode me. Will it not soon be night? Day. Night. Sometimes it seems to me the earth must have got stuck one sunless day in the heart of winter, in the grey of evening. Come on, Billy. You're beginning to embarrass me. Is there grass anywhere? I see none. Is there no green anywhere? There's a little moss.
These two short excerpts are from two works, both of which were developed to explore the possibilities of modifying a virtual acoustic system to incorporate feedback generated by that system. The non-clapping sounds in the first excerpt and the non-piano and non-vocal sounds in the second excerpt are this feedback. So why are we interested in this, and how are we doing this? Musicians, artists and technicians have explored the incorporation of audio feedback into recorded and live performances for at least 60 years. That being said, for the purposes of this study, rather than exploring feedback usage in popular or song-based music traditions, we will focus on the use of feedback phenomena as the primary, or at least a significant component, of the sonic materials in live experimental sound practices. As we mentioned in our paper, a full discussion of the use of feedback within live experimental sound practices is not the purpose and is beyond the scope of our work. For those who are interested, there are many sources to explore in this area, but perhaps the most comprehensive survey on this topic is presented in Cathy van Eyck's 2013 book, Between Air and Electricity, and on her associated website. For now, as in our paper, we suggest that most of the ways of working with feedback in experimental music practices are best encapsulated in the following works. So Pendulum Music by Steve Reich, 1968, Empty Vessels by Alvin Lucier, 1997, Cathy van Eyck's Wings from 2008, The Speaker Feedback Instruments, an ongoing project by Leslie Flanagan, starting in the early 2000s and still continuing, and Nicholas Collins's Pea Soup, originally from 1974 and has been revised in various ways from about 2001 until 2014. Perhaps what all of us are attracted to, that is to say, what we share with many of these experimental artists, is a desire to explore the notion or perhaps create an aesthetic situation which gives the impression of artists just playing with air. Thinking about works that fall into such traditions, the following ideas and questions arose in our minds. Given that audio feedback is the result of a positive loop gain between one or more microphone inputs and the output of one or more speakers, And given that the acoustic properties of the performance space or the system will determine the feedback frequencies that can result, that is to say, the most likely audible feedback frequencies being determined by the lengths of the direct and early reflection paths between the microphones and the speakers, then, within the fixed geometry of a performance space, how might one go about modifying the acoustic characteristics of this space so that different qualities of feedback, or a wider variety of feedback frequencies, can be achieved with minimal intervention and minimal additional processing? It was quite clear that by exploring feedback within the context of virtual acoustic environments, we could do just that. Before jumping into virtual acoustics, let's quickly review ways to generate, control, and ultimately suppress feedback. While some artists do like to explore squealing or howling feedback sounds in their work, to shape feedback, to give it in some way a slightly malleable feel, it is helpful to know how to suppress it and or dynamically turn it on and off. Often, to utilize feedback in performances, we use techniques such as EQ bandpass or notch filtering, dynamic processing with compressors or limiters, frequency shifting, simple or complex phase or polarity inversion, physical gestures or motions which change or attenuate the feedback, changing the geometry of loop gain paths in a performance space or within an instrument, and using piezoelectric microphones rather than air microphones. All of these techniques are used to varying degrees in the works of Reich and the others that we've mentioned so far. Given that virtual acoustic systems require many microphones and speakers to operate in close proximity, similar ways must be found of suppressing the many potential loop gain pairings. Therefore, the architecture of typical virtual acoustic systems could allow for feedback to be dynamically turned on and off during a performance. When using virtual acoustic systems, the audience and performers have the sense that they are hearing sounds in a space other than the actual or the expected acoustic of the physical space they occupy. With these systems, in both commercial and academic settings, the simulations or oralizations are likely to have the acoustic characteristics of a specific concert hall or room, or perhaps an acoustic characteristic of a religious temple, church, or large cathedral. Thus, we might think of microphones and speakers of a virtual acoustic system as being placed and forming potential virtual geometries of such spaces. Of course, if virtual acoustic environments are dynamic, that is, we can constantly change the virtual space, then with minimal interventions, the feedback produced in these situations is no longer dependent on a fixed geometry. However, virtual acoustic systems are generally very expensive, so who's going to let you play with these? Over the last few years, we developed a virtual acoustic system, one that was easy to install, uninstall, and calibrate, one that can operate with a variety of commonly available microphones and speakers, and one which requires no specific proprietary hardware or software. The virtual acoustic oralizations are generated with low latency convolution reverbs, and when running, musicians can interact and move freely in the virtual acoustic spaces without the use of headphones or close microphones. While developing this system, we found two ways or interventions that temporarily destabilize it. When we stop the interventions, the system resets and restabilizes by itself. We noticed that as the system resets and stabilizes, the feedback decays into the virtual environment, similar to how such frequencies might be expected to decay in the actual space. The first method to destabilize our system involves temporarily blocking the microphone speaker signal path by placing a hollow object such as a cup, a drum, a box, etc. over the microphone. The resulting feedback is colored by the resonance of these objects as well as that of the virtual space. A second method, requiring no physical intervention, is achieved by inserting a variable delay into the feedback cancelling signal path, that is, the path used for the elimination of loop gain feedback conditions between our virtual acoustic system's microphones and speakers. If we delay this canceller signal, the cancelling will be misaligned in time from the signal it is intended to cancel, causing a reduction in the amount of feedback suppression. And so we get feedback associated with the digital lengthening of the microphone loudspeaker paths filtered by the cancellation signal and the oralization simulation, the reverb of the virtual space. In both of the initial sound examples from the beginning of this talk, we used this cancellation signal delay method. In the first sound excerpt, a 2-microphone, 4-speaker virtual acoustic system was used. This was done inside the Karma listening room using 4 of the speakers from the upper ring, with a microphone suspended in the middle of the room. we inserted the delay on only a single microphone and speaker combination. In the second sound excerpt, a single mic and speaker system was used, which were placed inside a disc lavalier. It is worth noting that in this first sound example, the virtual environment is stable. In the second sound example, it is dynamic. That is, it is continually changed as the piece goes on. It is important to mention that in our paper, we present both methods of system destabilization and restabilization in a reductive form. As seen here, we cover and uncover the microphone of a single speaker and microphone virtual acoustic system. And here we demonstrate our delayed cancellation signal path method of feedback generation on a similar simple system. In this simple configuration, we trigger a signal, a 300 millisecond pink noise burst, through the virtual acoustic system speaker. Each time we trigger this noise burst, we simultaneously change the amount by which the feedback cancellation signal path is delayed. Thus, feedback tones are introduced whose frequencies are determined by how the virtual acoustic simulation is articulated by the noise burst and by the amount of time by which the cancellation signal is delayed. We then reset the delay to 0, restabilizing the feedback cancellation signal path. This causes the feedback to decay in a manner similar to how such frequencies would decay in the actual space as auralized by the virtual acoustic system. So thank you, and let us know if you have any questions.
Hello, my name is Karolina Pravda, and I am a doctoral candidate at the Acoustics Lab of Aalto University in Espoo, Finland. And today I am going to present to you the work that I did together with Sebastian Schlecht and Vesa Välimäki, the evaluation of reverberation time models with variable acoustics. So to begin with, reverberation time is the time needed for the sound energy to decrease by 60 dB from its original level after termination of the excitation signal. So this definition was formulated by Wallace Sabine over 100 years ago. However, it is still used nowadays, and the reverberation time, or T60, is an important parameter in room acoustics. However, this definition is good when we measure the reverberation time. However, how do we estimate the T60 in a room that maybe is not even built yet? So Sabine came up with a formula for estimating the T60 of a room, in which he took into account the room's volume, the area of the surfaces in the room, the average absorptivity, and the absorption of the air. However, the problem of the Sabine's formula is that for it to be accurate, the room must fulfill a list of requirements. First of them being that the sound energy must be equally diffused throughout the space, which means that walls should not be parallel, and there should be no big differences between the basic dimensions of the room. Also, the average absorptivity should be low, and the absorption should be uniformly distributed in the room. To improve this formula, Eyring came with his own model that is based on the mean free path between sound reflections and is suitable for rooms with high absorption. However, both of those models still assume that all surfaces of the room have the same average absorption. So to address this, Millington and Sete came up with their own formula, which does not assume that all the surfaces have the same absorption. It works well for the rooms with the surfaces that have different absorption. And further improvement was done by Kutruf, who assumed statistical distribution of the sound in a room and also took into consideration the room's shape and absorption distribution. However, all of those models, even though they acknowledge that the surfaces have different absorptions, they still assume that those absorption coefficients are more or less the same. So the first model that included geometrical aspects of the sound field with unevenly distributed absorption was introduced by Daniel Fitzroy. He assumed that there is a relation within 3 possible decay rates along the 3 basic axes in a rectangular room. A similar idea was introduced by Arau, who described the T60 as a geometric weighted average of the reverberation times in 3 orthogonal directions. Even further improvement was made by Neubauer, who noticed that both Fitzroy's and Kutruf's models were based on the concept introduced by Eyring. So he made a similar correction to Fitzroy's equation as was earlier done by Kutruf to Eyring's formula. And this correction was split into 2 parts, one for the ceiling and floor, and the second for the remaining walls. So to check whether those formulas work in real life or how do they work, we conducted measurements in the Variable Acoustic Lab ARNI that is located at the Aalto University. The lab is equipped with 55 variable acoustic panels that are located on the walls and on the ceiling. The variable acoustic panels look approximately like that. They have a metal frame and slots cut out in the front surface. The slots can be closed and therefore the panel is reflective, or they can be open, so the sound can enter the panel where it is absorbed by the absorptive material. So we did measurements in 2 scenarios. In the first scenario, first configuration was where all the panels were open, and then in every next configuration, the panels were closed one at a time until all the panels in the lab were closed, meaning that the first configuration, all panels open, then the second, 1 panel closed, the third, 2 panels closed, and so on and so forth. And the direction of closing the panels is indicated here by the arrows. And in the second scenario, we still started with all panels open, but then each configuration, in each configuration, only the panels on the ceiling were closed one at the time. If you want to listen to the examples of measured impulse responses, please visit the publication's website. So having the measured values and also the ones calculated by the models that were presented before, we wanted to compare the results. And what we did was we calculated the reverberation times for 6 frequency octave bands. And here you can see an example of the plot with results. So the vertical lines on the plot indicate the end of one wall and the beginning of the next wall, as you can see here. This is the first wall, the second wall, the third wall, the fourth wall, and the rest is the ceiling. And also on the x-axis, you can see that the number of closed panels increases, which means that the absorption decreases in that direction. So here you can see the results for all the 6 frequency octave bands from 250 Hertz to 8 kilohertz. And as you can see, Except for the 250 Hz band, in all other bands, the models underestimate the T60 values in the room. Also, what you can see is that in many bands like 500 Hz, 1 kHz, and 2 kHz, when the absorption decreases, there is a non-linear increase in the reverberation time. And most of the models cannot repeat this increase. So what we did next was we calculated the absolute mean difference between modeled and measured T60 values and converted them into percentage. So as you can see in this figure, the Fitzroy's formula provided the best results and gave the smallest error, which in the best case was around 17%. The worst predictions, or the biggest error, was given by Millington-Sette's formula most of the time, and when the absorption decreased, Arrow's formula gave a bit worse results. So the same comparison we did for the scenario in which panels only on the ceiling were closing, and as you can see, the plots look a bit similar, and also on the x-axis, as the number of closed panels increase, the absorption decreases. So you can see here the full results for the 6 octave frequency bands, and the results are pretty similar with the first scenario, meaning that for the 250 Hz band, the modeled and measured values of T60 are somewhat similar, but in every other band, the modeled T60 values are much lower than the measured ones. And we again calculated the absolute mean difference between modeled and measured reverberation time values. And again, the Fitzroy's formula provided the best predictions, except for when the absorption decreased considerably, where the Sabine's formula is a bit better. And the smallest error in the best case was around 16%. And again, the biggest error was given by Millington-Sette's formula. So knowing that the models for predicting reverberation time that were presented in the study depend heavily on the absorption coefficient values, we wanted to check whether our results and our conclusions are valid or are correct. So what we did was we added noise to the absorption coefficients of floor, walls, and curtains. And we ran 1000 simulation where in each simulations the values of the added noise were different, and they were ranging from minus to plus 50% of the initial values of the absorption coefficients. And after this 1000 simulations, we could say that the story that we wanted to tell didn't change, meaning that most of the models still underestimate the reverberation time, and also that the Fitzroy's formula still gives us the smallest difference between the modeled and measured values. Here is a example of the plot with results that we made after this 1000 simulations. And if you want to see more, please visit the publication's website. So to conclude this presentation, as we could see, the models to predict the reverberation time are quite inaccurate. And in our case, the best predictions were achieved with Fitzroy's formula. However, the biggest errors were given with the Millington-Sette's model. What was surprising is that this 100-year-old Sabine formula performed actually pretty well. However, one of the most important conclusions here is that a more accurate and flexible method for estimating the T60 is definitely needed. So here you can see some references that I used in my work. And I thank you for your attention, and I hope to receive some questions from you. Thank you.
Hello to everyone. I'm Luana Strepi. I'm a researcher at Polytechnic of Turin, and I welcome you to this session. Which I'm really glad you could follow. And I would also like to thank the three presenters for their interesting works. And I would go on with a few questions. So I would warmly invite you to write on the chat on the YouTube channel your questions. I've seen that someone has already started. For our first presenter, I would start with a question. Regarding the HRTF accuracy in measurements, how much accuracy is required in order to perceive the difference? You have done a lot of work into the details of the measurement points and so on. How necessary is all this, and to which aim, I would say?
Yes, so basically, I think I also mentioned it in one of the slides. We investigate based on something called psychoacoustically valid data point predictions, and that's was found in previous work to be around plus minus 10%. So depending on the frequency, you have to be within a range of plus minus 10% of your target frequency. But of course, this is just some previous work, and we don't know the setting of those experiments exactly. So I think ideally one would move on and use these results and do some sort of a perceptual evaluation and try to compare with this previous work, and also basically evaluate our own models.
Mm-hmm.
Yeah.
Yes.
But yeah, in the paper it's roughly plus minus 10%.
Plus minus 10%. And yes, my further question on this was how much the number of listeners or the number of testers that you investigate influences this accuracy. So is there a size effect on this?
And this limit of plus minus 10% for the psychoacoustically valid.
Yes.
I'm not sure right now about that particular paper from where we took this reference, how many persons they had in their tests, but I would imagine that it shouldn't be dependent on the number of people that you test. Of course, like if you would just test a very small amount of people, you would have some statistical randomness. So it might be that sometimes it would be more or less, but if you test enough people, you should somehow converge to this value that they talk about.
Mm-hmm.
Yeah.
Any other questions from the audience? Because I have a lot of questions on this topic. It's very interesting.
Yeah, I mean, I'm looking.
There's a question to Carolina, if I might chime in.
Yes.
It's on the YouTube chat.
Carolina, are you planning on making your own reverberation time formula based on our measurements?
Well, maybe I am not planning to do it myself because, to be honest, it's quite a complicated task to like come up with some model, especially that, as you can see from my presentation, most of these formulas still most of those formulas still miss something. They still can't be really accurate. So I think that there is something really more, much more needed than just let's say simple formula. But I've heard and I know that some researchers are working to provide better estimates of reverberation time in the room. So there is that research coming, and when it comes, I'm sure to have it also tested in our variable acoustics laboratory.
That's very interesting. And I would also add, if have you also planned to test a combination of absorption and scattering surfaces? As you might have read, there are a lot of there is a lot of research nowadays that is studying the combination of these two kind of materials, since they influence a lot the sound field. And therefore also the sensitivity of these formulas is related to these conditions and how these two kind of materials are combined.
Yes, so there are plans to see how different type of surfaces, like more diffusive, more the ones that more scatter sound more, how they affect this reverberation time for formulas or the accuracy of predictions. However, well, this is just something that we plan now. For now, we can't like for this paper, this presentation, we couldn't provide such research because like for now we don't have that type of space that would have, let's say, the controlled number of diffusion that we could change. Like here we change the absorption, the amount of absorption. So we don't yet have like similar space where we also can have the control over the scattering of the sound. So we hope that we'll have that space in the future so we can explore this topic some more.
And yes, we have also another question on this. Do you think that measuring different rooms would lead to different conclusions? And I think here with different rooms, maybe it's meant that different volumes, and we would expect that with different volumes or shapes, you might lead to other results. Have you tested this in a preliminary way?
We haven't tested that yet, but I agree that, of course, like different volumes, different shapes will affect the accuracy of this reverberation time formulas quite a lot. However, also kind of my argument is that those formulas are very widely used also in kind of commercial use. So to predict reverberation time in smaller rooms, in classrooms. So it's I think worth to say that we should be very careful when maybe predicting the reverberation time with the rooms that are That's reverberation time formulas were intended for. That we should not maybe, based on those results, like trust them 100%. So, but I agree that probably for rooms with like bigger volumes, they could be more accurate. Yes.
Okay, thank you. Is there any other question? I would ask our second presenter whether you have tested the influence of the background noise on your system. How it would influence the adaptivity of this method?
Good question. Well, if something is audible when you turn the cancellation off, anything that's audible is going to contribute to what comes out. And so, for example, in the piece in the disc clavier, the fan noise is quite close to relatively close to the microphone. So a little of that seems to bleed in to the feedback that is produced. In terms of the overall feeling of reverberation in the system without us messing around trying to generate feedback, it doesn't seem to have a large effect. The background noise, like once you calibrate in the room and things are relatively stable, it stays the same. Temperature, put it this way, drastic temperature change makes a larger effect to the feedback cancelling than anything else that we've experienced. We haven't tested that as such, but we have noticed when we crammed a bunch of people into the studio and the temperature went up, you could really get a difference. Whereas everything else seems to be, so far, has seemed to be fine. We haven't totally tested all of that.
And which do you think there are the limits of this method?
Say that in another way. So the limit would be in the shape of a room in terms of if the listener is very close to a boundary wall and they're obviously getting the actual reflections of the space that they're in, that can be quite distracting. Is that what you mean? That's one limit of what we're doing. The other limit, say, would be within the piano piece as well. You've only got a single speaker generating, so it's not so much generating an acoustic as in a kind of an effect. It gives a sense of prolonging the decay of the piano. It gives a little bit of sense of kind of, oh, there's another space, but it's not the same as having 4 speakers around you and being immersed to a certain degree.
I see.
Okay.
Okay.
Yeah.
Is there any other question? Thank you. From the virtual audience? No? Maybe there was the question from our Skype chat. If you want to answer to that.
Oh, somebody asked me about the feedback on Beckett. I would say, yeah, there's a little bit. So somebody asked me if there is a connection between feedback and Beckett in the work. I suppose in terms of the theatre circular kind of idea, and in a lot of those pieces as well, there's this the dialogue. You know, what's the famous thing about Beckett? Like, you know, he manages to do nothing twice, but within that nothing, within each kind of section of that, there's these little waves, these little peaks of kind of energy, and then it dissipates and goes away. So that kind of that rhythm is kind of built into the plays, and it just makes it really, really useful when you're trying to generate feedback. And there's certain moments where the voice raises up, catches on when we turn the feedback system, when we turn the cancellation off, and just, yeah, we tried a lot of other material for that kind of speech generating feedback. That rhythm that's inbuilt in the Beckett stuff just works really, really well. And yeah, so that's why we did that.
Okay. Well, thank you to all for attending. I will give the word to Andrea.
Okay, here I am, and thank you all. Thanks to all our speakers, to our Chair Luena. I'm just here to tell you that it's been a long day, but I think it was been very rewarding. Now, in terms of scientific program, we will be back tomorrow, and tomorrow in particular at 12 Central European Summer Time. And I have to remind you that, of course, this evening is not finished yet, because at 9:45 there is the first music session. We have 6 pieces that will be streamed on our channel, and in particular this music session is devoted to binaural pieces. So wear your headphone and listen to those pieces. You have 1 hour right now, and you can then be back here on our channel. So thanks to all, thanks for your work, and see you later and tomorrow. Bye.
So,
Proseguendo impotente, proseguendo impotente, proseguendo aspettando in basso, in basso, So, proseguendo in potere, proseguendo in potere, proseguendo